Welcome to Mastering Wireshark 2 video course by Pact Publishing. My name is Andrew Krauthamel. I've been an IT engineer for over 10 years now. About half of that I've been a senior network engineer for various organizations. I'm also a Cisco Academy instructor and perform additional educational and video instruction as well. Check me out at andrewkrauthamel.com for additional information. In this video we're going to go over the Mastering Wireshark 2 course and what you're going to learn by going through it. Learn about the Wireshark 2 interface, completely redesigned and reprogrammed in a new language to be more consistent throughout its user experience. Learn how to capture packets in various different ways and for various different reasons. Follow data streams and view the data that's contained within. Dive deep into analyzing many different common protocols. Learn how to create and interpret I/O graphs to pick out potential issues within your data flows. Learn how to view and interpret statistics for many different protocols. View and analyze protocol communication flows to pick out TCP handshakes and potential issues. Learn how to create capture and display filters to pick out exactly what you want to see in a capture. View VoIP calls and play them back in order to hear exactly what the user hears. Learn all of these skills and more in Mastering Wireshark 2 to make you an excellent network engineer. Welcome to Section 1, Installation and Setup. In this section, we're going to take a look at installing Wireshark on Windows and installing Wireshark on Mac and Linux. Welcome to installing Wireshark on Windows. In this video, we're going to take a look at how to install Wireshark on Windows. Your first step is to go to the wireshark.org webpage. When you get there, scroll down on the home page and click on Download. When you click on Download, the latest version of Wireshark will be visible. Select the installer for the version of Windows that you are currently running. Most people on a modern computer on a modern version of Windows will be running 64-bit. If you happen to be running an older version of Windows on 32-bit or older hardware, make sure you select the 32-bit version. If you're not sure which one to use, do the following. Open your control panel, go to System and Security, and click on the System link. In the System section, you'll see here it says System Type 64-bit Operating System. If you have a 32-bit, it'll show that here as well. Back on the Download Wireshark page, download the version that you need, and run that file. And click Next to begin the setup. Read the license agreement and click I agree, and select the features of Wireshark that you wish to include. Most people include all of the defaults. You'll see here that we have the main Wireshark application, we have the classic interface version of Wireshark, and we have T-Shark, which is a command line version of running Wireshark, as well as some plugins, the user's guide, and some additional tools. We'll go ahead and accept the defaults and click Next. And in this window we can go ahead and customize what shortcuts show up and whether file extensions are associated to Wireshark. I'm going to turn off the Wireshark Legacy. Go ahead and click Next and select a location for Wireshark to install. I'm going to select the defaults here as well. And on the next page here it says, should we install WinPCAP? WinPCAP is the driver that allows Wireshark to interface with your network card. WinPCAP is required for it to be able to view all the packets. So if you don't have WinPCAP installed, leave that checked and it will install it as part of the install process. Go ahead and click Next. You can also install USB PCAP, which allows you to view the traffic on a USB connection. Most people won't need this, so we'll leave that unchecked. Go ahead and click Install, and Wireshark will now install. Partway through the install, the WinPCAP installer will then run, and we'll go ahead and click Next. Read the license agreement, click I agree, and you can decide whether or not you want the WinPCAP driver to run at boot time. Most people allow it to do so. We'll leave that as defaults and click Install. That will finish very quickly, and click Finish. The Wireshark install will then continue. When the text window says completed, go ahead and click Next, and then you can select whether or not you want to run Wireshark at that moment and click Finish. Once the Wireshark GUI loads up, you are done. In this video, you learned how to install Wireshark on Windows. In the next video, we'll go over how to install Wireshark on Mac and Linux. Welcome to installing Wireshark on Mac and Linux. In this video, we're going to take a look at how to install Wireshark on Mac and how to install Wireshark on Linux. To install Wireshark on Mac, start by going to the wireshark.org webpage. When you're at the webpage, scroll down on the main page and click on Download. The latest version of Wireshark will be displayed. Go down to macOS 10.6 and later and click on that to download. At this point, we can choose to save the file to our Downloads folder and then open it, or simply open it directly off the web page with the disk image mounter. Go ahead and click OK. It downloads the file and opens it up. We can then double-click on the PKG file and click Continue. Read the license agreement and click Continue again, and click Agree that you agreed to the license agreement. If you wish to change the install location, you can do so now. Otherwise, click Install. Enter your administrator credentials and click Install Software. Once the installation is successful, click Close, and you can close this as well. If you go to your applications list in the lower right and scroll down, you should see Wireshark at the bottom of the list. You can select Wireshark, and you can see that it's now loaded. Once Wireshark is up and running, that's it, you're done. Installing Wireshark on Linux will differ based on the distro that you're using. Here I'm using one of the most common distros available, Ubuntu. In order to install Wireshark, we're going to go to the Ubuntu software application. Go ahead and click that. And we're going to search for Synaptic. Synaptic is a package manager similar to the Ubuntu software application, but it gives you more control. And for some reason, at the current time of recording, Wireshark is not showing up in the Ubuntu software application, but it does show up in Synaptic. So we're going to go ahead and install Synaptic. Simply click Install. Enter your administrator password, your root password. And the software is now installed. You saw it shake over here in the bottom left. Go ahead and click on Synaptic to open that up. Enter in our credentials again. And now we have our Synaptic application loaded. This is again very similar to the Ubuntu software application, but it's less pretty. Click on the search button and we will search for Wireshark. Enter Wireshark and click search. And you'll see everything that has Wireshark in its name or description now shows up in the package list. We're going to scroll down and select the main Wireshark package. So none of the other packages that have dash something, just the one that says Wireshark. So we'll select that, click on that and select Mark for installation. It will then ask you if it's okay to install other packages that are required. We can say, sure, that's fine. Mark them for installation as well. So now all of our dependencies will be installed as well. We can then go up and click Apply. And it's going to tell us that we're going to install the following packages. Click Apply again. And Synaptic will go ahead and download and install all the programs that we've selected. At one point, you'll receive a window pop up asking you if non-super users should be able to capture packets. I would recommend selecting yes. That will allow you to separate your root user from your standard users, but still allow you as a standard user to capture packets. Once everything is complete, you'll receive a Changes Applied window. It'll say Successfully applied all changes. You can now close the window. Simply click Close, and you'll see everything here marked in green is now installed, including Wireshark. So at this point we can close this program and we can close Ubuntu software as well. Next, click the search button in the upper left of the interface, and we're going to type in Wireshark. And you'll see as I type there, it automatically shows that Wireshark is here. We can simply click on that and that will load Wireshark. At this point, once Wireshark loads, you're done. In this video, you learned how to install Wireshark on both Mac and Linux, specifically Ubuntu. Our next section is getting started. Welcome to Section 3, Filtering Traffic. In this section, we're going to take a look at BPF syntax, which allows you to limit the packets and frames that are received by your capturing interface. Capture filters, where we're going to take that BPF syntax and apply it to interfaces and show some examples of limiting the captured data from an interface. Display filters, where we're going to limit what is shown to us from a capture, which may have more data than we need. Follow streams, which is a great feature of Wireshark and allows you to follow a TCP or UDP stream, and it will automatically filter the traffic for you and show you the data enclosed in that conversation. And advanced filtering, creating additional columns, filtering based on certain fields within a packet, things that many people don't know that they can do in Wireshark. BPF syntax. In this video, we're going to take a look at the Berkeley packet filter, known as BPF, and its syntax and some of its history. So let's talk about the Berkeley packet filter history. Many years ago, we're talking decades here, every operating system had its own packet filtering API. There's a number of examples listed here, such as Sun, DEC, SGI, Xerox. They all had their own operating systems, and each operating system had its own API for capturing and filtering packets. So when you needed to do network analysis, you had to use their specific software with it built into the operating system, their specific filtering capabilities within the API that they designed. That made it very difficult because depending on the implementation of your network and what different operating systems were involved, you had to know all these different APIs and all of these different filtering rules in order to get anything done. So in 1993, Stephen McCann and Van Jacobson, they released a paper titled the BSD Packet Filter, or BPF. And they really outlined the rules and the ideas behind BPF and how it could be a standardized method for filtering captured traffic. It just so happened that it caught on and became very popular, especially as libpcap and winpcap and other libraries out there began to utilize BPF as its standardized filtering system, and especially the use of Wireshark nowadays that utilizes those libraries. In order to write BPF, we need to create an expression. And an expression contains one or more primitives. And in BPF, primitives are an ID, such as a name or number, an IP address, an Ethernet address, something like that, plus a qualifier. And a qualifier has three pieces to it. We have the type, the direction, and the protocol. So for a type, it could be an individual host, a network, a port range. The direction can be either the source or the destination, the source or destination, the source and destination, and the protocol, whether it's Ethernet, FDDI, wireless LAN, IP, IPv6 nowadays, ARP, RARP, DECnet, probably not so much, TCP, UDP. You have to define these different pieces that you want, how you want to limit your traffic, and the values that go with them, the ID, the name or number, to go along with these qualifiers. So I have some examples here for you so that it can make some more sense as to how to create a BPF expression. The first one is IP host 192.168.1.1. So the IP is the protocol, the host is the type, and the ID is the IP address. So that will filter the traffic for that IP address, whether it's the source or destination. That host keyword does both of those for us. Next up, I have Ethernet source and a fictitious MAC address. Same idea as IP host. We're defining Ethernet as our protocol, source as the direction, and the MAC address that we're looking for. If you happen to be capturing traffic that has multiple VLANs, such as spanning a port that's a trunk port on a switch, you can specify the VLAN or VLANs. The next example is Ether broadcast. And this one has a special keyword being used of broadcast to tell BPF that we want to filter all of our traffic, whether it's a broadcast of some kind, on layer 2. And my last example is TCP port 80. So we're going to filter that traffic, looking for HTTP traffic most likely, looking for only port 80 of any source destination. Up next is capture filters, where we're going to take this BPF syntax and apply it to interfaces within Wireshark. Welcome to video 2, capture filters. In this video, we're going to take a look at how to filter traffic before it's captured with BPF syntax. So we're going to filter that traffic on the capture interface. In Wireshark, there's 2 places to enter a capture filter. The first one is right here on this main screen. Right here in the middle we have the capture section, and it says using this filter, enter a capture filter. So we can actually do that right here on the main screen, and then remember when I double clicked on my interface, after I enter a capture filter, then it will start capturing with that applied filter. You also see that there's a green bookmark icon here. If you hover over that, it says Manage Saved Bookmarks. And if we click on that, there's a number of saved bookmarks that are already built into Wireshark. So if there's a common function that you want to filter on, it may already be in here. But you can also go up to the top and Manage Capture Filters. And this gives you a list of all of your predefined capture filters and any that you have saved yourself. So you don't have to keep entering the same capture filter over and over again. You can create one and save it here. So all you do is click on that plus icon, and then you can enter in whatever it is you want to do. So we could do IP host, and we've now created a new capture filter. And then of course I can rename it. If I double click on that, that will allow me to rename, and I can say my host. Then if I go back and look, it's now visible. You can also save a capture filter by selecting an interface first, then entering what you wish. And you'll see it turns green if it's a valid entry. And then click on that bookmark icon and go to Save This Filter. If you click on that, it'll then bring up the Manage Capture Filters window, pre-populated, so that you can simply name it as you wish. Then using this capture, I can simply double click on my interface and begin capturing that traffic. And you can see I'm filtering on Ethernet broadcast here, so it's only going to show broadcast traffic on layer 2. The second way of entering a capture filter is through this gear icon that I previously mentioned. Click on Capture Options, and then you'll see down at the bottom there's the capture filter for selected interfaces, and you can enter the capture filter just like you did on the previous window, as well as manage your bookmarks. So we could enter in IP host, select the interface, and then it'll turn green, and then I can start my capture. And now it's going to show me any traffic to and from my gateway. Our next video is display filters, where we're going to filter our traffic after the capture has already been started or it's already been saved, rather than filter the traffic during the capture itself. This is a very common method of doing things, so that you capture all the traffic on your network and then simply view only the pieces you need. In our last video, we went over capture filters, how to prevent certain types of traffic from getting into our capture in the first place, or restricting the capture to a specific address or something like that. In this video, we're going to go through display filters. And in regards to display filters, we're going to talk about how to sift through a large packet capture. So a common method of capturing traffic is to not use the capture filter and instead capture everything that the interface can see, and then simply filter out exactly what you want to view, because some of those other packets may be useful in diagnosing some sort of a problem. We'll also go over quick access filter buttons. So if there's a common thing that you need to filter on all the time in your environment, you can create a quick access button and simply click on that, and you don't have to type out the display filter every time. Now there's a number of filter operators that you can use to combine multiple filters to create a full expression as to what you want to specifically filter on. So you could combine IP address filter with a port number filter, or something related to TCP, or something related to 2 MAC addresses. And you can combine them or exclude them in different ways using these filter operators. You can use either the word version of the operator, which is what's before that slash, or after the slash you can use whatever's listed there, which is like the mathematical equivalent of the word option. Now you see in the bottom right there's also a parentheses, so you can also combine filters together and their operators, kind of like a mathematical equation, so you can have certain comparisons such as two ors be compared first and then have it with something else as an addition, such as an and. Okay, so to work with display filters, let's get some traffic first. I'm going to start a capture on my primary interface without any capture filters. And so now we have some packets coming in. So this is whatever's idle on my system at the moment. And you see up at the top here, we have a apply a display filter entry box. And it also has that bookmarks icon, just like the capture filters does. So let's get some packets to work with. I'm going to start a capture on my primary interface without any capture filter entered. So we're going to capture everything that's occurring on my system currently, whatever's in the background. Okay, so we have a good amount of traffic here to work with. I had opened up a window in the background to Google, so we have some web traffic to look at as well. And you may have noticed up at the top here we have a text box that says apply a display filter. And that works just like the capture filter text box does, and we can type in whatever the display filter is that we're looking for. We also have the bookmarks icon on the left, just like with the capture filters, and if I click on that, that gives me my saved filters. And I can have a whole bunch of them listed in here. These are the common ones that come with Wireshark pre-built. And just like with the capture filter, if I enter one in here into the text box, I can save it, or I can go in and manage my display filters, and I can add and remove them manually in here as well, just like with the capture filters. So let's start off by filtering by something. So let's do IP.host, and we're going to do equals 192.168.77.1. So that's going to be my gateway. And I can then either click on the arrow up here to apply it, or push enter. And when I do so, here's all the traffic to and from my gateway, 77.1. Now I can also do source or destination. So you'll notice here I use the keyword host. So IP.host. Host is a shortcut to have it include both source and destination traffic for a specific IP address. I could also do source, which is src. But if I do it this way, I'm only going to get the traffic originating from 77.1. I'm not going to get the return traffic. Same thing if I do destination, DST. I'm going to get the return traffic, but I'm not going to get the originating traffic. So how do I get this traffic? I can chain it together using one of those operators like I mentioned. So we're going to tell Wireshark we want both the destination and the source traffic. So we have IP dest up there already. So what we're going to do is combine it with an OR. And if you remember, you can either type OR or the two pipe symbols. And we'll do IP.source equals, and actually, you know what? Instead of doing EQ, remember we can do the equals symbols as well. So you get to see both. And we'll put in the IP address of my gateway. And now that it's a valid display filter, it's turned green, and I can just push enter. And there we go. Now we have both directions of traffic, just like if I typed in IP.host. So you can see how using some of these shortcuts that you know of in the display filter options can make things faster for you. Another interesting one that we could do is, let's say we need to troubleshoot something with a slow transfer with TCP. So we want to look at window size. It's TCP.windowSize value, and you can see I already entered one in here in the past, is less than 10. So if the window size is really small, I'm curious. I want to know about that. I'm curious. So we push enter, and there we go. So we have one packet. Remember, we didn't define any sort of IP address here. It's any of the packets that this thing is captured that has a window size less than 10. Show that to me. And so here we go. Here it is. And if we expand our TCP details, you'll see there's the window size. It's certainly less than 10. So let's create an example using those parentheses I mentioned. So what we'll do is filter based on my gateway again. What I'm going to do is quick access one of my last used display filters. So I'm going to type IP, and if you look there, it has the most recently used up at the top. So I'm going to use the down arrow, select the one I want to use, and push enter. And there we go. So now we're filtering on my gateway again. We're going to add some parentheses to that. So I'm going to add an end parentheses and a beginning parentheses here. And now I'm going to add in DNS. So I want to see any traffic to or from my gateway, and it's a DNS entry. So I'm going to do and DNS. So this is a shortcut here for the DNS protocol. I push enter, and there we go. So here's all the traffic to and from my gateway that happens to be DNS. Now we can go even farther. So we can say and IP.length do less than or equals 72. And so now I've trimmed it down to any DNS packets to and from my gateway that are less than 72 bytes in length. So you can see how this is really powerful and how you can trim out exactly what you want to see. Now this is a very powerful feature with a lot of filters in it. In fact, there's tens of thousands of filters for, I think it's 2,000 protocols now. So if you go to wireshark.org/docs/dfref for display filter reference, that will show you all of the different fields that you can use. And you can see they just keep going and going and going. So what we'll do is we'll click on I, and we're going to look for IP. There we go. We click on that, and then that's going to tell us all of the subfields that we can filter on. So IP is the protocol, and now we're curious about maybe the address or the checksum. What else do we have here? We've got destination, source, types of flags. Flags are very important as well. We'll get into that later on. GeoIP information, all sorts of things. So this is a great reference to search for what you wish to filter by. Now the last feature we're going to talk about in this video for display features is creating those quick access buttons. So if you look over on the right, we have a plus icon, and it says add a display filter button. So if we click on that, we can then create a label and enter a filter to save. So let's say I want to make one for my gateway. I'll make a filter of ip.host equals my gateway. And I click OK, and you see there it is. I have a button for gateway now. So if I have a big capture with hundreds and thousands of packets, I can simply click on my gateway button, and it instantly applies that filter. Then of course I can create additional ones as well. So maybe I want everything that is DNS, and so we'll use DNS. And so instead, show me all of my DNS packets. Now if you wish to remove some of those buttons, I found the easiest way to get there to simply click the plus icon again, and then there's a button on the left here where it says Filter Expression Preferences. That will jump you directly into the Wireshark Preferences section for this, and then you can just edit or remove whatever buttons you don't want or you need to change. You can just click OK, and then that goes back to defaults. So in this video we went over the basics of the display filter and creating quick access filter buttons. Up next, we're going to talk about filtering by TCP and UDP streams and showing specific conversations within our packet captures. In our last video, we went over how to use display filters to limit what you have to see in a packet capture. In this video, we're going to build on that and follow streams. What that means is, in this video, we're going to follow TCP and UDP streams to pick out conversations within our packet capture so that we can view those specific communications between each TCP communication or each UDP communication. So what we have here is a packet capture of opening up the Cisco.com homepage. And the Cisco.com homepage is not encrypted with SSL by default, so we can see all of the HTTP communications within it without having to add in some sort of SSL key to decrypt it. And we can see here in the beginning the DNS query to Cisco and the response from, and then the beginnings of the TCP handshake, and we start to retrieve some files and some HTTP traffic for retrieving HTML. Now, we could, of course, apply what we learned in the last video and go up to the top and create a display filter for the web server as the host and the TCP protocol with maybe some other parameters to try and filter out what we want to see, but we're still going to have a whole lot of data here. You can see this is a very large capture just to load up one web page. So, how can we pick out individual communications within this packet capture? Because one thing you'll note is in a web page you have multiple files, graphics, maybe some CSS files, JavaScript, whatever it might be that it needs to retrieve, and there's a number of different files it has to pull in order to build the web page that you see, embedded videos, whatever it might be. Each one of those is its own communication. Each one is its own TCP stream. So what we need to do to use TCP or UDP follow stream is to select a packet within the capture that is within the stream that we wish to view. So for each of these individual files in this web page, each one's going to be its own TCP stream. So we need to select a packet within that and then follow the stream. So let's choose one of these graphics here. So here's spinner.gif. So here's a GIF file that is within the Cisco web page, and you can see on the left here, in one of the first videos you learned that there's a related packets diagram on the left now, but it's not as helpful since this continues on and on and on. So what we want to do is follow this stream instead. So let's go up to our spinner.gif. Here's our HTTP packet. We're going to right click on that and go to follow TCP stream. And I'll resize this a little bit for you. There we go. By default, the data shows up in an ASCII format. And that's usually very helpful to you because a lot of the traffic you're probably looking at is text-based, but you may wish to change that when you're doing this follow stream. You can do that at the bottom here where it says show data as ASCII. You can change that drop-down box and select whatever data format you wish. We'll leave it as ASCII here since we're looking at some HTTP traffic with a GIF transmitted within it. And you can see here we have red and blue. Red is the client and blue is the server. You can see that at the bottom where it says 16 client packets, 228 server packets. We can also change this drop-down box and select the communication that we wish to look at. And as we scroll down in this data view, you can see the blue and red of the client and the server sending their packets back and forth. And as you may have noted in one of the earlier videos, if you click on the data, it will jump to the packet in the packet view. An additional feature of the follow TCP, an additional feature of this window is that you can print or save your packets. So you can actually export these and save them as whatever file format you deem. You can also follow UDP streams. Now, UDP streams are more difficult to follow though, so it may not always work perfectly, but Wireshark does the best that it can. The reason being is the difference between TCP and UDP is that TCP is reliable and UDP is unreliable communication. And you can see that if you were to go into a TCP packet and you expand the TCP section here, you go down and look at the sequence number and acknowledgement numbers. That's how Wireshark is tracking that communication, by following those numbers. Because as you go through, you can watch those acknowledgement numbers and sequence numbers change as you go through a stream. Whereas UDP does not have such a thing. So, Wireshark does its best to try and determine what is a conversation within UDP, but again, it may not be exactly perfect. So what you want to do is the same thing as with following TCP traffic. You right click, you go to follow, and now you can see that UDP stream is available for us to click. We select that, and it will do the exact same thing. It will show the data up in the top pane. It may be useful to you, it may not, depending on what kind of data it is. And it will allow us to do all the same features as follow TCP stream. In this video, you learned how to follow TCP and UDP streams to pick out specific conversations within your packet capture and data flows. Next up, we have advanced filtering, where we'll get into picking out more nuanced sections within a packet capture and within your packets to enhance your ability to filter your traffic. Welcome to video of Advanced Filtering. We're going to go over how to filter traffic on data fields within packets, how to create columns on specific fields in our data packets and to sort them, and filter with these more hidden methods that you may not have noticed yet. Okay, we're back in our packet capture, opening up cisco.com, and what we're going to do is expand this section here that gives us the details of our packet. And what we'll do is scroll down and find a packet that we wish to investigate a bit more. So let's find something down here. Here's an HTTP OK. What we can do is expand these sections here, which will allow us to view easily the different fields of data within the different layers of the packet. So if you're familiar with the OSI layers that we use in networking, then this will look familiar to you. So we have our layer 2 information with our frame and Ethernet. We have layer 3 with IPv4. We have layer 4 with TCP, and so on. So let's click on TCP here to expand this, and we'll go down to window size. Now window size is an important field that we'll get into in more detail later on, but what we'll do is view this as a column. So let's right click on that and click on Apply as Column. And what that will do is add a new column in our packet list with the window size value for each packet. Now you'll see it right aligned here, and with that right up against the information, it's a little bit hard to see. So let's right click on that header up there and go to Align Center. You click on Align Center and that makes it a bit easier to view. Now what we can do is click on that header and it will sort our packets from smallest to largest or largest to smallest. Now this is very useful to see because many times with transfer issues you'll have a window size problem. So it might be beneficial to you to sort this way and look for any window sizes that are, say, 0 or something very small, depending on the packet. Not every packet that's small in its window size is a bad thing, but it's something useful that you could take a look at. Now you can do that for almost anything in here. We can go in and make columns for almost anything. So we could find another good one here. We'll do the status code on HTTP. And we can do Apply as Column, and then we'll sort by status code. And there we go. Now we see all of the 200 status code HTTP packets, and if we scroll up you'll see some additional ones as well. So that's a very useful feature. Additionally, we'll remove these columns. We'll right click, go to Remove the Column, and remove the column. And additionally, we can go into TCP, for example, or any of these fields, and we can create filters based on what we see here. So it's much easier than going in to the display filter field and trying to find exactly what you want to do. Because as I mentioned before and showed you the website, there are hundreds of thousands of these different things that you can look for. So instead of doing it that way, you can do it visually with these packet details here and select what you want to filter on. So let's clear out our display filter, and we can filter on, let's say, header length. So we'll right click and go to Prepare a Filter, Selected. What that will do is prepare a filter in that top section with the header length information selected. So I click on that and it has tcp.headerLength, so that's a shorthand for header length, equals 20. Now if I apply this, it's only going to show header lengths that are 20 bytes exactly. What if I want to change that? I can of course go over here, and as you saw before in the operators and such, you can change those, and then we can go ahead and apply that. And so now I have all the packets listed that have a header length less than or equal to 20. Well, let's find another one. Let's go to TCP again, and we will scroll down and we'll look into the flags, and let's do any acknowledgements. So let's right click on acknowledgement, and we'll go up to the top here to apply as filter. Now the difference between prepare and apply is prepare puts it into that top field, the display filter field here, but doesn't apply it. apply does both. So if you know exactly what you want, you can just go straight to apply. So let's apply selected. So with doing that, we now have all of the TCP acknowledgement packets listed. Now we can also expand that. And let's go down and find another one. Let's find another flag. So there's an acknowledgement, and we're going to add push. So we want to see all the packets that are acknowledgements, but also are push. So we're going to right click on push, and we're going to, let's apply as filter and selected. And you can see that it applied all of the syntax that's required to make this work. So it takes a lot of the heavy lifting out of creating filters. So now we're looking at all of our packets that are acknowledgements with the push field set. So I'd like to show you another feature here. What we will do is we're going to create a filter for my gateway again. So there's ip.host equals my gateway here. And we apply that, and that's all the traffic to and from my gateway. And let's sort it by number here so it makes sense. So here's from the beginning of the capture to the end. Okay. What if I don't want to see the DNS? So what I can do is go to DNS, right click on it, apply as filter, and not selected. And what that will do is negate that selection. So I select that, and you can see in the syntax it does and bang, the exclamation point, DNS. So anytime you put the bang symbol, the exclamation point, in front of something, that tells Wireshark that you do not want to see that. So now I am only seeing SSDP here. So I can also do that for any other field. It doesn't have to be DNS. So we could say we want to look at all UDP, but not 405 bytes in length. That's a very specific thing to filter on, but you can do it. And that's a great feature that you can really prune out exactly what you want to see. So I highly recommend you spend time going through these packet details, learning where they are, what you want to look for, and getting used to using apply as filter and prepare as filter, and understanding how they work together. And you can really take a packet capture that has hundreds and thousands of packets in it and trim it down to just a few dozen that you actually care about. In summary, in this section, you've learned about BPF syntax, the history of it, and how to create BPF syntax, how to use that BPF to then apply it as a capture filter and reduce the packets that you end up capturing on your capturing interface, how to create and use display filters to prune what you have in a packet capture to what you just need to see, how to follow streams, both TCP and UDP streams, so you can view specific conversations within a packet capture and export that data if you wish, as well as going into the different packet fields and lengths and all the different pieces of data within the headers of the packets, and able to create filters based on those. Our next section, we're going to start tweaking Wireshark and really customizing it and creating your own preferences and profiles so that you can make Wireshark your own. Welcome to section 4, customizing. In this section, we're going to take a look at preferences, how to customize Wireshark and improve your workflow by tweaking some options within Wireshark. Profiles, which are sets of preferences and colorizing rules and things like that, which make your analysis in different protocols and different scenarios easier. And colorizing traffic, which allows you to adjust the coloring rules that are already there by default that you might have noticed to better bring to light different issues that occur in your packet captures. So let's get into preferences. In this video, we're going to take a look at how to customize Wireshark to your needs and preferences in different scenarios, and discuss recommendations about those types of scenarios as to why you might want to enable or disable different preferences that we'll go through. To access Wireshark's preferences, go to Edit, Preferences, and that will open up the Preferences window. And on the left, you'll see that there's a number of categories that you can choose from, and that breaks up the preferences so we don't have 1,000 preferences all on one page. And the first category is appearance. And in appearance, you can change a number of settings, including the default folder that you most commonly open files from, and changing the filter entries and recent files values. And what those do are probably the most common things you'd want to change in this section. And the filter entries changes the number of filters that appear in this drop-down box. We're at the display filter section. So right now there's 10, and if we close this, you'll see you click on this drop-down with the arrow. This is the last 10 that I've entered. You can change that so it shows more, and that's what that preference does. Additionally, we have recent files, and that's based off of the file menu. If you change that to a higher value, then your Open Recent will show an additional number of recent files. Down near the bottom of this section, you'll see Main Toolbar Style, and it says Icons Only right now. And if you're new to Wireshark and you're watching through this video series to learn all the ins and outs of Wireshark, you might have noticed that toolbar up at the top there with all the icons. They don't tell you what they are unless you mouse over them. You can change that so it says icon or text or icons and text. That can be pretty helpful for someone who's new to Wireshark. It'll tell you what all those buttons do without having to spend time to mouse over each one. So if we click OK, you'll see that it's much more verbose with its description as to what these buttons do. Another helpful section in here is the layout underneath appearance. And this layout section, you can change how that default view looks like within Wireshark. You might have noticed that as I've done captures previously in this course so far, that it breaks it up in Wireshark in 3 panes, and the 3 panes are on top of each other, the top one being the list of packets, the middle one being the details of a selected packet, and the bottom one being the bytes. And so if you don't like that and you want to change how it looks, either in overall organization or remove one of those panes, you can do that in here, and you can see a number of options across the top as to how you might want things broken up. And then you can also change which ones are in which panes and whether or not you even want any to show up, such as some people don't really care about the packet bytes, we only care about the list and the details. So you can certainly go and turn off the packet bytes if that doesn't, if that's not something that you need. Now, in the advanced filtering video, we went through how to create columns in Wireshark, and this is another way of doing so in editing those columns. So while you can right-click on a field within the packet details, as I showed you before, to create a column out of it, you can also create your own custom ones in here, or reorder or remove the different ones that are already there. You can, of course, customize the fonts and colors within Wireshark, but these are separate from the colorizing rules that we will get into later on in this section. Under the capture category, you can choose a default interface. Now you've noticed before that I have a number of interfaces on my system. You can select your favorite interface or your most commonly used interface on your capturing system if you do so very often. So I might want to choose my gigabit adapter for my examples here, since I use that interface most commonly to create the examples that I show in this course. You can also in here turn on and off the PCAP-NG format, which I would highly recommend that you leave it enabled, since that is now the new standard format. But if you have a requirement to capture only in the old PCAP format for some reason, for some legacy software or something like that, you can certainly do so. To improve performance in Wireshark, you may want to turn off these 2 options, updating the list of packets in real time and automatically scrolling in the live capture. You've noticed that in the captures that I've done so far, the second you click capture, it starts scrolling through in that packet list, showing you everything that's coming in at that moment. Now that is useful for small captures and quick ones, but if you have a system that's receiving a lot of data, maybe it's a span port on a heavily used trunk or something like that, or the system is old and it potentially could drop packets because it doesn't have the processing power to do that, you may want to turn this off to preserve your performance in Wireshark. Your next section in the preferences is the filter expressions, and we've gone over that in a previous video. This is where all of those expression buttons will show up. Our next category is name resolution, and Wireshark allows you to resolve many of the different addresses that we see in Wireshark into different names to make it easier for us as humans to understand what we're looking at. So by default, it allows for resolution of MAC addresses to the first half of the MAC address. If you know about MAC addresses and how they work, the first half of the MAC is the manufacturer of the network card. So Wireshark has a built-in list of those known manufacturers and those OUIs, which is the first half of the MAC, and it will try to resolve them for you. And that's why you'll see potentially Realtek : and then the other half of a MAC address or something like that, or Cisco : and the last half of a MAC address. That's because of this checkbox. You can also resolve the transport names, which are the TCP and UDP ports, and IP addresses. Now, if you choose the IP address option, note that it does not reference a static file within Wireshark like the MAC address and the transport names. It will attempt to do DNS resolution while you're capturing. So that can be a very negative thing with Wireshark, especially if you are doing a large capture with a lot of data coming in. You could have potentially thousands and thousands of DNS resolution requests going out from your capture system, clogging up the works. So what I would recommend is instead, what you can do in the packet details, when you have a capture, you can right click on an IP address and resolve it with that specific IP address rather than resolving everything. Now the lower section here where it says enable OID resolution, suppressing SMI errors and things like that, these are for SNMP resolution. So in SNMP you have MIBs, which are basically word translations to OID locations, and you can resolve those in Wireshark. If you are capturing SNMP traffic, you can resolve those OID strings into the MIBs if you enable OID resolution. Our next category is protocols, and when you expand the protocols category here, you have a huge list of all the protocols supported by Wireshark and all of their associated configuration options that you can tweak. Now most of these you can leave alone at their defaults and everything will work just fine. There's two that you're probably going to want to tweak at some point in your career, and that'll be IP and TCP. All three if you count IPv6 now. So IPv4, IPv6, and TCP are probably the most common ones that you're going to adjust if you adjust them at all. So what we'll do is we'll go to IPv4, and you'll see there's a checkbox here that's actually disabled by default. Now this used to be enabled by default, so depending on the version of Wireshark you're running, if you are not using the latest version of 2.0, the validate the IP4 checksum would potentially be enabled, and when it would do that, it would sometimes show up based on your system with a whole lot of bad checksum errors. And the reason for that is that a lot of newer systems, especially servers, have been starting to do checksum offloading, where the software does not do the checksum creation, but the hardware does right before it gets sent onto the wire. And so Wireshark didn't see that, and so it always thought that the checksum didn't match because it couldn't see the hardware creating the checksum as it got put onto the wire. So that's one thing to go in to check, is you most likely will want to have that off nowadays due to most network cards doing checksum offloading. And our next category is statistics, and there's not much in here that you're going to want to change. I would leave most of this alone, unless possibly you'd want to change the number of channels in the RTP player. Our last category is advanced, and in the advanced category we have a listing of all of the preferences and settings within Wireshark in a nice big list for you. So if there was something that you needed to change but maybe you had a problem or something like that and you found an answer online to change a value and you don't know where that is within the interface, you could do so by going in here. And what's nice is there's a search function if we needed to change something. You can filter it and determine where a certain setting is. Our next video is profiles, where we're going to take preferences and colorizing rules and things like that and create custom packages of them as profiles for different needs for different situations. In our last video we went over preferences and how to customize Wireshark to your needs. In this video, profiles we're going to take a look at how to create profiles to package those preferences into usable profiles that you can switch between based on the situation that you are in. When you're using Wireshark, any of the changes that you make to it, whether it's your preferences that you might be changing, or display filters that you might be creating, or capture filters, or any of that, they all go under what is known as the default profile. And when you create new profiles, they will work as a copy off of the default profile. So it's recommended that you make minimal changes to your default profile, if maybe a few overreaching changes for your environment, but don't do anything specific, and instead make a profile for different specific situations that you might need. And you can do that in the bottom right-hand corner of the Wireshark interface. You see there's the profile default selected there. And if you click on that, it'll allow you to select between the different profiles that you have on your system. And by default, you have a classic and a Bluetooth profile that's included in Wireshark. You can see we're currently using the default. If you wish to manage these profiles and create them, you can right-click on that same location. And you'll see there's now a new window that pops up that allows you to manage your profiles or create one. They take you to the same spot though. So what we'll do is we'll just go into Manage Profiles, and here's our listing of profiles that we currently have. To create a profile, we just have to click on the plus. Or if you were in that previous window, you could simply click New, and it brings you to the exact same window, but instead it automatically clicked on this plus for you. So what we can do is name our profile here. So we'll call this New Profile. And you'll see that it says down here, created from default settings. So that's what I was talking about, how it copies the default settings, whatever you had already configured in your system. And it's now created a new profile for us. And if we click OK, it will now, you see some things changed here in the interface. And in the bottom right, it says Profile, New Profile. So we're now using that. What you can do is right-click on that again and go to Edit. And you'll see here it has the path to the profile. Wireshark stores profiles as folders. So click on that and it will open up the profile folder. And we're going to go back one. And you'll see here under the Profiles folder, every new profile that you create will show up as a new folder in here. And if you go back even one farther, you'll see here's the default files that have been created in your Wireshark installation. And there'll be different ones depending on what you might have changed. So for example, there's C filters here, which is your capture filters, and we can show that. Remember those capture filters, they're under your capture options, and if you click on this bookmark, it's an easy way to get there. And you can manage your capture filter. So here's the capture filters. Remember I made a custom one in here at one point previously. That's why it has that saved. Additionally, we have I/O graph preferences. We have language selections now that Wireshark is in multiple languages. We have the recent files and preferences, as we were just using in the previous video. And another one would show up here if I created a display filters. There would be a dfilters file too, which would have customized display filters. Now what we can do is we can edit these files as well. These are text files. What you can do is right-click on it and edit the file. I would recommend using something such as Notepad++ that will show the carriage returns correctly, because if you open it with Notepad, it might not show up correctly due to the type of carriage returns they use. Now, if you wish to share your profiles with other people, you can go into the Profiles folder and simply copy this folder for whatever profile you wish to share. Maybe you have an 802.11 wireless one, or a TCP analysis one, or a corporate network one, major errors one, whatever it is that you might have, and you have multiple IT administrators or analysis individuals that are in your organization, you can share these profiles amongst each other by simply copying and pasting these folders between your different computers. And you could share it as a zip file or whatever suits you best. So in this video we went over how profiles work in Wireshark and where they are stored and how to share them, and what kind of files and changes and preferences and filters that are included within a profile. And up next we're going to talk about colorizing in Wireshark, which is also included in a profile. Welcome to Colorizing Traffic. In this video we're going to take a look at how to create coloring rules, how to remove them, how to make your own, how to colorize conversations, and filter traffic by the coloring rules that are applied. Here I've pulled up one of the previous captures that I've done loading up a web page, and we're going to use this as an example for our coloring rules discussion. And you can see here that it's already been colorized by default from Wireshark. So I mentioned before in the profiles and the preferences section there are default settings within Wireshark, including for coloring rules. So Wireshark tries to make it a little bit easier for you to view your traffic even from just a standard install, but you can of course customize that to show what you want to see, and that's what we're going to talk about over these two videos. The first thing you want to know, besides the fact that Wireshark will automatically colorize your traffic from a basic standpoint, is that you can enable and disable the rules with one button. Up at the top of the window you can click on this button here that looks like kind of a rainbow color of lines, and you can click on this to enable or disable the coloring rules in bulk. So if I click on this and disable, now everything turns to white and there are no coloring rules currently applied. And if you click on it again, it will re-enable the coloring rules. In order to get to the coloring rules, you're going to go to View and Coloring Rules. And by clicking on that, that'll bring up the coloring rules window. And here you see the default selection of coloring rules that are created by Wireshark at installation. You can see how the default rules have some real vibrant coloring rules right at the very top. And these are some of the nasty ones that you want to keep an eye out for. And that's why they have a black background. That way they stick out in this default pastel coloring system that they have for the other traffic. So you can see most of the other normal stuff like ARP and ICMP and SMB and HTTP, UDP, all of them are a nice color. They're a pastel type color, and then all of a sudden you have this black show up with red text. You know, that's obviously something bad. You have the yellow show up, you have the bright red with the TCP resets and the aborts, and you have checksum errors that are black with a red text. They're supposed to stand out on purpose. Another thing to know about this is that you see how the bad ones are up at the top. The rules are processed from top down. So it's based off of a matching system. So if something matches first, then that will be applied. So if you have two rules that are very similar, and maybe you have two rules that look for ICMP but have different colors for some reason, the one at the top is going to be applied first, and then the one below will be skipped if it's already been colorized. Additionally, on the left-hand side of all these coloring rules are a bunch of checkboxes, and these checkboxes enable and disable these individual coloring rules. That way you don't have to enable or disable all of them at once with that button I just showed you. So you can just turn off the ones you want or don't want. So for example, what we can do is we can turn off HTTP, which is this nice light green color you can see throughout all of our capture. If you look at the scroll bar here, remember, so there's all of our packets that are green. So I'm going to turn that off. We're going to click OK. When I do so, you can see they all turn into purple. Now why do they turn into purple? So let's go back to our coloring rules and we'll take a look. And if we check here, where's purple, this nice light purple? Ah, there it is, TCP. So yes, all those communications, all those packets are TCP packets. So remember I was talking about how things match first on this list towards the top? So obviously the HTTP traffic, which is more specific, since that's a higher level protocol, matched first and then was applied green. And then when it matched for TCP, it was ignored because it was already colorized. So you can kind of see how you want to put more specific things towards the top and then more generic things towards the bottom. And you can see how it's kind of broken out that way already with all these very specific filters up at the top and then the basic ones at the bottom, such as TCP, UDP, and such. So we can turn this back on. And additionally, you can create your own, of course. So in the bottom left, just like the other windows we've seen already, you can click on the plus button, and then that will create a new coloring rule. And you can see it puts it up towards the top for you as well, which is very nice. And here you can enter any sort of display filter you want to create a color. So we could say ip.host is my gateway, since I like to use that as an example. And we can choose a foreground and background color. So down here at the bottom, we can choose a foreground and background color. So let's make it something completely ridiculous. The foreground is going to be bright pink. And the background will be a hideous yellow color. There we go. So that definitely stands out, doesn't it? So we'll say, okay, well, let's rename it first. We'll say gateway, and we'll click OK. And now you can see how all of the packets that reference my gateway are now colored in bright yellow. Now, just a minute ago, we were trying to figure out which coloring rule applies to a specific packet. And we were doing so by going into the coloring rules and trying to just figure it out by ourselves by going down the list. Now, you don't have to do it that way. There's an easier way of doing it. So I'm going to remove this gateway here and we'll click OK. Now we're back to the standard coloring rules. If you click on a packet that you want to investigate and find out, okay, well, why is this green? We can look in the packet details, and under the frame section, we can go down towards the bottom of the frame information, and it will show us the coloring rules that are applied. So here's the coloring rule name, HTTP, and the string that applies to it. Now, if you make a whole bunch of custom coloring rules for your specific company and your certain situation that you have going on, you can absolutely import and export those to share them with coworkers. So let's go back into our coloring rules, and you can see here in the bottom right of the window we have an import and export button, which will export it or import it through a text file. Additionally, we can colorize conversations. So what we can do is we'll go and select a random packet in this conversation here, and we can right click on it and go to colorize conversation. And then we can break down on which conversation we want, which layer of the OSI model. Is this layer 2 that we want to colorize? Do we want to colorize layer 3? We want to go up to layer 4 and so on. So let's say, for example, I want to colorize this conversation between these two IP addresses, and we're going to make it a, let's say, a yellowy color. We click on that. Now this one conversation is now yellowy color. So as you can see, this conversation coloring application that I've just done has caused the entire packet capture essentially to become yellow, which is not as helpful to us. So let's get more specific. Let's go up the OSI model. So what I'll do is I'll select this packet, and we're going to colorize the conversation, but do it from the TCP conversation. And I'll go ahead and make it this pink color. And when I do so, you can see that one conversation for that TCP connection has been now colorized pink, and the others have been left green. And I can go ahead and colorize another one, and we'll do another conversation. We'll make that one red. And here you can see how you can keep picking out conversations and colorizing them differently. And finally, one more cool feature I want to show you is you can go ahead and actually filter on coloring rules. So let's select a packet here, an HTTP packet, and we're going to go into that frame section in the packet details again, and I'm going to right click on the coloring rule that is applied to this packet, and I can go to apply as filter selected, and I'm now filtering on that coloring rule. So it's not just on the fact that it's HTTP traffic, but it's on the coloring rule applied. So we can do that to another one as well. And what we'll do is we'll select this one, the pink one we made, and we'll go to the conversation color filter, and we're going to apply that as not selected. And now we've just filtered out that conversation based on the coloring rule. So in this video, you learned how to view the coloring rules, how to add and remove the coloring rules of your own, how to import and export them, how to colorize by conversations, as well as filter by those colorizing rules. Up next is colorizing traffic, where I'm going to go through some examples as to how you can use coloring rules to your advantage to pick out bad things in different packet captures. Welcome to colorizing traffic. In this video, we're going to take a look at some examples of how to show specific issues in your packet captures with colorizing rules, and that should hopefully improve your analysis speed. In this example, I've just tried to open up a web page that is to a non-existent location on MIT's website. So there should be a response code from HTTP in here stating 404 that it couldn't find that file. So what we're going to do is create a coloring rule that will easily show that error message in the packet list here. As we scroll through, it'll pop out to us. So you can see we have mostly standardized colors here. We got purple and some green in there from TCP. We got a few black ones, which are nothing we have to worry about here. But that's it. So let's go into our coloring rules, and we're going to create a custom coloring rule for HTTP response codes. So what we'll do is we'll type in http.response.code and is greater than 399. Now, all of the HTTP response codes that are above 400 are server and client errors in the 400 and 500 range, respectively. So we want to see all of those errors in a very vibrant color. So what we'll do is we'll go in and make it, you know what, we'll pick this pink here. Do for the background color. So the background is going to be bright pink and black text for the foreground. You'll see that's right up at the top there in our list, so that'll be applied first. And let's click OK. And we'll scroll down through our list here looking for that bright pink packet. Hopefully, we will see it show up. Oh, and there it is. Pops in real easily, very visible to us. So you can see here it says HTTP 404 not found, and we can expand in the details here and take a look at that, of course. And we'll expand that even farther. And you'll see the status code of 404. Then if we take a look at the frame information, remember we can see that the coloring rule is applying that new coloring rule that we created. Now a second example we'll take a look at is with DNS. So let's say, for example, you have some sort of problem in your network where certain DNS responses are coming back that they can't find any sort of records in your DNS server for a resource, whether it's a web page or a local server, whatever it is, it's not finding the DNS entries. We can apply a coloring rule that will vibrantly show us whenever there's a DNS response that it cannot find a record. So let's go ahead and create a new capture. And I'm going to look up some random web page that doesn't exist. And we'll use DNS off of Google. And there we go, it can't find it. Excellent. So we're going to stop our capture. And you'll see here nothing really pops out. There's some red stuff there from some TCP resets and some black ones, but nothing else. It's all TCP traffic and DNS. So let's go ahead and create a coloring rule. And we'll make a new coloring rule. We'll actually name this one this time. We'll call it DNS no records. And in the filter information, we're going to enter DNS.flags.rcode, which is for the response code, and if the response code equals 3. So whenever there's a response code of 3, that means that there's no record. And I'll show that to you in just a second. So we can go in and make this a very vibrant color for us. There we go. Bright yellow looks good to me. We don't have any other yellows in our coloring list, so we'll go ahead and apply that. And let's go ahead and scroll through our packet capture here. I have a lot of traffic on the system right now, so that's why we have a large packet capture. And let's see if we can find this response code error. Oh, and there it is. So we can see there's our standard queries, no such name, a record, and then the random gibberish that I entered in. And then of course it's also responding for IPv6. The AAAA, the quad A record, is for IPv6 as well. And if you take a look in our frame information, there's our coloring rule, DNS no records. There's the string that it's using. And if we dig into the DNS information here, you look at the flags, and it will say reply code no such name. So that's that value of 3 that we just filtered on. So you can see how applying coloring rules can be very helpful to someone who's doing network analysis and protocol analysis, because it makes it very easy to pick out from a large packet capture wherever there's a problem. So in this section, you've learned how to apply preferences in Wireshark and customize it to your needs. You've learned how to create profiles for different analysis requirements, and you can switch between them. For example, the coloring rules that we just did could be put into a profile specifically for DNS or specifically for HTTP. And you've learned how to create those coloring rules, how to import and export them, how to apply them to real-world examples. Our next section, we're going to dive into statistics within Wireshark, which is a great feature that very few people seem to use. Welcome to Section 5, Statistics. In this section, we're going to take a look at TCP/IP, just a general overview, what it is and how it operates, time values and summaries, how to take a look at the difference in time between packets to diagnose and troubleshoot things. We'll also look at all of the great statistics that are available from Wireshark, and we'll take a look at the expert system in Wireshark, which is a great feature that allows you to take a look at the errors and critical issues in a packet capture, and it'll bring them right up front for you, easy to view. This is video 4.1, TCP/IP overview. In this video, we're going to take a look at the basics of TCP/IP, how packets are built, and the resolution processes that are in place, such as DNS and ARP. In networking, we have two models that we commonly use, OSI and TCP/IP. On the left side, we have the OSI model, and on the right side, we have TCP/IP. And I've tried to match them up so that you can see how the different layers of each model line up with each other. Now, detailed training on the OSI model and the TCP/IP model and the basics of networking is outside the scope of this course, but I just wanted to reference it real quick since we use it in Wireshark on a day-to-day basis. When we use Wireshark, we're commonly concerned with layers 2 through 7 of the OSI model. And most commonly, when you use Wireshark, it's probably because something weird is going on, and that usually when something weird is going on, that's often application related, or the system running an application. So most commonly you'll find yourself using Wireshark to diagnose problems that are in the upper layers, especially layer 7. But you can certainly use it to troubleshoot connectivity issues between devices on layer 3 or layer 2. And while there's a number of TCP/IP services and protocols that we use to help us communicate over a network, know that we reference the layer that that protocol resides on based on the OSI model, not the actual TCP/IP model's layer. What I'd like to do is run through the building of a packet, which will give you an idea as to how the values are entered into a packet for the different fields. And since we're looking at those fields in Wireshark, it's certainly a good thing to know. So what I've done is in a browser, I've opened up a connection to pbs.org. And what we're going to do is follow through that connection and show how it found the resource and then sent its first data packets to it. So the first thing that your system does is it needs to figure out what port number to use. So when you open up your web browser and you go to pbs.org, depending on how you enter the address up into the address bar of the browser, the application of the browser is going to know whether or not you want to use port 80 by default for HTTP, or port 443 for SSL, or maybe some other custom port. So right away, your computer knows what port number that it needs to start communicating on. Since I went to pbs.org without any sort of SSL connection, it by default knew that it was going to have to use port 80. The next thing it has to do is figure out where that service is. So I went to pbs.org, but my system didn't know where pbs.org resides. Remember I mentioned that the DNS? So remember that I mentioned that DNS deals with the resolution of a name to an address. And so my system took a look at the DNS cache on my local system, which is a rolling cache of addresses that it has already resolved, and it looked for pbs.org. And it saw that pbs.org didn't exist in the cache. So it said, okay, I need to go send that out to my DNS server to get a hopeful response of where this resource is located. My DNS server happens to be on my gateway, which is 77.1. This is common for standard home networks. It may not be there. It could have been a remote resource as well, such as a Google DNS server or OpenDNS or some other. If this is a remote DNS server that I'm trying to connect to, then my system is going to take a look in my route table and figure out where does it need to go in order to access that DNS server. So if it's remote outside of my network, it's going to take a look at my route table and realize that it has to go out through my gateway in order to go talk to the DNS server. And when it does so, it's going to check my ARP cache to see if there's a layer 2 address for my gateway so that it can send a frame to the gateway. If my system didn't have ARP cache entry for my gateway, then my system would have sent an ARP packet out looking for the physical address for 192.168.77.1. My system happened to have it in its ARP cache since I commonly access that IP address, and so we don't see an ARP packet here. What we do see here is the first packet is a DNS packet. So my system saw that it was 77.1 was my DNS server, and it knew that it was a local resource. It checked my route table. It realized that that's on my physical interface there. We're already connected to the 77 network, and I already had an ARP cache entry for 77.1, so it didn't need any of that information, and it automatically built the DNS packet. And then we can see in here in IPv4, my destination is 77.1. It built all that without having to produce any other packets to find this information. So my system then sent out its DNS request asking for pbs.org. And if we go down and take a look at the UDP section here, you can see that we're using port 53, which is for DNS. And if we expand DNS, we can look at the queries, and we can see that we're asking for pbs.org. We then have to wait for the DNS response. And we see the next packet here for DNS. We receive a standard query response for pbs.org. And if we look at DNS in the packet details pane, we can take a look at the answers in this packet, and you'll see that pbs.org has a CNAME entry for this address, and then there's an A record entry at this IP. The A record entry is what we care about. So now my system has an IP address for pbs.org so that I can build a TCP handshake to pbs.org to the web server so that it can then begin flowing HTTP data back and forth. So if we look at the next packet in line, we have our SYN. So this is the first packet in our three-way handshake for TCP. If you're familiar with TCP at all, it goes SYN, SYNAC, ACK, and that's your three-way handshake to open up a connection. So my first packet here has a destination address of 54.243.141.169. If we look at that response that came back in DNS, that's the address that was provided for the A record. So now my system knows what IP address to craft its TCP packet for. So we have a source of my local system, destination to the server for pbs.org that it received, and then it sends out its handshake request. It then gets a SYN-ACK in response saying, yes, I see your connection request, let's create a connection, and then my system responds saying, yeah, that sounds great, I acknowledge. And then finally we begin our first HTTP packet. My system sends an HTTP packet out to that same server and says get HTTP. So it's saying please send me your beginning index.html and any other data for the HTTP resource. And again, it knew that it needed to use port 80 HTTP unencrypted because when we entered that into the browser application let the stack know that it was using port 80. And so that's the basics on how a TCP packet is built, and your system requests a resource from some sort of server or other device out there. Up next, we have time values and summaries. There's some great summary information panes that we can take a look at, and we can use time to help us diagnose problems in a packet capture. Welcome to video of time values and summaries. In this video, we're going to take a look at how to change the time settings for packets and troubleshooting with the time column. Here we have the PBS packet capture again, where I opened a browser and went to pbs.org. And if you notice in the packet capture, the second column says time, and it's a number with a decimal, and it just keeps counting up as you scroll down through the packet capture. By default in Wireshark, this is the time since the capture started. Having the time since capture can be useful so you know when certain packets arrive in relation to the entire data flow that you captured. But it's not all that useful for trying to diagnose a problem where there might be a delay in a certain service returning traffic back to your system that you're trying to capture. In order to figure out the delay between captured packets, you'd have to look at this and figure it out based on milliseconds and microseconds and nanoseconds. And that's not that great for humans because we're not all that great at math to that level. So what we can do instead is go up to View, Time Display Format, and we have a large selection of time display formats we can choose from. And the most useful one that I would recommend is using seconds since previous displayed packet. That way, if you apply a filter on your traffic, such as following a TCP stream or something like that, it will show you the delta difference between each packet based on the applied filter. If you use previous captured packet, then if you have packets that are filtered out from the view that you're looking at, then it's not going to coincide exactly with what you're looking at. It makes it a little bit harder to understand. So what I would recommend is choosing displayed packet, and now if we look, the time column has changed and we have 0 seconds between each packet, and then there's some sort of fraction of a second for each packet for the delay between each captured packet. And what we can do is we'll scroll up to the top and you can sort that column, and if you sort it by highest to lowest, you can see what packets are the most delayed. Now if you select that packet and then resort by number, you'll be brought directly to that packet wherever it is within the numbered packets that you've captured, so you can look at the packets on either side of that packet to figure out what might be going on. You can also add additional columns. So what we can do is go to Packet Details, that lower pane of information, and expand the frame information, and you'll see there's a number of time fields here. What we can do is also add a column for one of these time fields. So what we'll do first is we'll switch our display format back to since beginning of capture, and we're going to add a column for the delta between each displayed frame. And so we'll do that by selecting this. We'll right click and apply as column. And then we can drag this column over to the other time so that it makes a little bit more sense. There we go. And so you have time since the capture began, and then time delta between each displayed frame. You can also go under View, Time Display Format, and change the fraction of seconds based on what you want to see. So maybe you don't need to see the nanoseconds and you only care to the milliseconds. You can change that manually here, and you can see how it pruned our time column. You can also add columns by going to Edit Preferences and going to the Appearance Columns area, and you can manually add whatever column you want. Lastly, if you go to Statistics, Capture File Properties, you'll see a list of information based on the packet capture. And if you scroll down, you'll notice that there's a whole bunch of statistics here on the capture itself, including the number of packets, the time span, how big is this packet capture in number of seconds, average packets per second, average byte size, total number of bytes that have been captured, average bytes per second, and average bits per second. This summary can be useful when comparing a capture done during a benchmark when everything's running normally and compared to a packet capture performed when there's performance issues. You can see if there's any of those values in the summary statistics that have drastically changed. So in this video we learned how time works in Wireshark. what the default is, how to add a column for time, and how to view the delta between each displayed packet. Additionally, we looked at the summary information so you can see the total statistics for a packet capture. Our next video is trace file statistics, and we're going to go through all of those statistics windows that are available in a packet capture. Welcome to video trace file statistics. In this video, we're going to take a look at how to display useful statistics in Wireshark and some issues you could troubleshoot utilizing that statistical information. In order to access the statistics in Wireshark, click on Statistics and go to Resolved Addresses for the first one. And the Resolved Addresses window will give you a list at the top here of all of the IP addresses and DNS names that were resolved in your packet capture. So you can get an idea of all the different resources that were accessed in your packet capture. Next statistics we're going to look at is protocol hierarchy. When you click on protocol hierarchy, it gives you a breakdown based on percentages of packets of the most popular protocols that it saw. So let's close some of this so it's a little bit easier to see. And you'll see up at the beginning here, everything that came in was a frame. Everything that came in that was a frame was an Ethernet frame. And then within that, we have a breakdown of what's within Ethernet. So we have some LLC frames, we have a whole bunch of IPv4, and a little bit of ARP. If we expand IPv4, we see that the most amount of packets that we received were TCP packets. Now this is useful because you can see all the different types of data that have arrived. So for example, if you're not expecting to see Canon or NetBIOS UDP frames, that's useful to see in here, especially if it were a higher percentage in the number of packets that it saw in the capture. Or let's say maybe you shouldn't be seeing any SMB traffic and you see a lot of SMB traffic. That could be some sort of a breach. Next we'll go to conversations. And in conversations, we have a list of all of the different Ethernet and IPv4 and IPv6 and TCP and UDP conversations that have occurred within this packet capture. So on layer 2, what devices have communicated to each other. On layer 3, within IPv4, what devices have communicated to each other, and how many bytes have done, and how many bytes for each. And you can pick out some that are larger than others here, such as 40,000 versus 121. And you can go to TCP, for example, and see all the ports that were in use for each of these conversations. Additionally, on all of these tabs, there's a duration. And that's very useful to see which are the largest and longest talkers in your conversations that have been captured. So you can sort by your duration and see which ones are sending the most amount of data. Next we'll go to endpoints. And endpoints is similar to conversations, but it's simply a listing of all of the endpoints, not just the connections between the endpoints as to which IP is talking to which IP or which MAC is talking to which MAC, but it's just a listing of all of the devices on each of the layers and the information about them. So we're not concerned about the conversation, just the endpoints, all the endpoints added together. And as you can see under TCP, for example, we have 76 versus the 42 for IPv4. And that's because my host computer here opened up a whole bunch of ports when I opened that browser and tried to go to PBS. Next we'll go to packet lengths. Packet lengths is useful to determine if you have small packet lengths, especially if you're having a window size issue and a lot of your data is smaller than it should be. What you want to look for is most of your data in the 1280 to 2559 range for packet length, because the maximum NTU is 1500. So if you see the majority of your data, like you see we have 40% here, are in that range, then that means most likely most of your data is being sent and received properly. If you have less of a percentage here and you have a large percentage of packets that are in a smaller packet length, then you might have a problem. Note that you will see a large percentage in the very small packet length there because that's a lot of the ACKs and control packets that you'll have. We'll also go to IO graph. And IO graphs is a great graphical representation of the amount of data that's flowing through the packet capture from the beginning to the end. And so you can see we have from the beginning of the capture here, when I clicked start on the capture, and then I went to my browser and I opened up my browser and I typed in pbs.org, and then I pushed enter, then we see the spike of traffic as it went and got that data from the content servers for PBS. And then that communication ended, and then I stopped the capture. If you have a consistent file transfer that's occurring, for example, and it's at a low I/O due to some problem, you can see that here in the I/O graph. And we'll get into the details of customizing this later on in future mod. A useful statistic for HTTP is if you go down to the HTTP section here and click on Load Distribution, that will give you a view of all of the servers that have served up HTTP traffic in the packet capture. And you can see how many servers were served up. So maybe if you're trying to diagnose a problem with a content distribution network, you could see that here. Or if you're trying to find out which server is being loaded the most because it has the most connections to it, you can also see that here. And you can add a filter in here as well if you need. If you need to do a lot of analysis of DNS traffic, you can go to the DNS statistics window, and it'll give you a nice listing of all of the different codes that are returned in DNS. So if you're having problems with your responses or you're getting a lot of errors when you're not expecting to receive any, you can view that here easily instead of filtering by DNS traffic and going packet by packet through all of them. One of the coolest ones is flow graph, and what we're going to do is filter our traffic by this TCP flow. So we're going to follow TCP stream and create a filter for that. And so now we've snipped out just a little bit of our traffic. What we'll do is go to Statistics Flow Graph, and we'll expand that. And by default, it shows all of the packets in our packet capture. So as we scroll through here, you'll see all of the flows, all of the TCP handshakes, the SYN, SYNAC, ACKs, all of the requests and responses. Everything is in here in a nice graphical format that you can use to diagnose your traffic. This is very useful for SIP traffic, for example. What we can do is change in the bottom left there where it says show, we're going to change it to displayed packets, and that's going to apply it for that filter that we have behind the screen. And you can see the communication here going from my computer to the server as I request for data, such as a SYN, and then we have the SYN-ACK response, and then the ACK response back to the server, and then followed up with a GET from my system, and then the response with the data that starts to come back to my client. It's a very useful way of graphically representing the data flows that occur within your packet capture. In this video, we went over the statistics in Wireshark and why you'd use certain ones in certain situations. And our next video is expert system usage, which is a great feature in Wireshark that allows you to view all of the problems, most of the problems, in your packet capture, all in a nice, easy-to-use interface. Welcome to video of expert system usage. In this video, we're going to take a look at the expert system in Wireshark, which is a great feature that not many people know about, and it allows you to easily find problems in a packet capture. So we're going to take a look at that now. You can follow along with the capture that I'm going to use by downloading the same one off of the Wireshark website. There's a great section of their wiki called Sample Captures that allows you to download captures that have been submitted by the community. And you can see it's a very large document here. So what we're going to do is search for error. And the first one here that comes up, CMP in HTTP with errors, if you download that and extract it, you can open up the PCAP file and follow along. And here we have our PCAP file from the wiki. And in order to get to the expert system, there's two ways to do so. The first way is from the Analyze menu. We click on Analyze and go to Expert Information. The second method is in the bottom left here. If you see the colored icon here, it's a yellow icon. This icon color will change based on the errors that are available in the packet capture. So if this is yellow, the highest problem in this packet capture is a warning. If this is red, the highest problem in this packet capture is an error. If it's blue, it's chat information or informational and so on. And if you click on that, it will bring up the expert information. What you see here is a listing of all of the problems that Wireshark has automatically found in the packet capture. Now the chat ones are usually just generic informational data that you don't need to see, so we can minimize those. Now on your packet capture, if you have warnings or errors, those are things you want to take care of. The errors are the most critical. Those are problems in the actual TCP communications, or there's a problem in the packet in some way. There's a malformed issue, a CRC failure, something like that. Warnings are usually application problems, weird responses, and spooky stuff like that. And Wireshark notices that and will then alert you to it with this expert information window. So not only does it show you what the type of errors and warnings that it finds, but it tells you what packet number it's available on. And you can click on it. So what we're going to do is bring this window over to the side here. And we have our packet list and packet details. If we click on packet number 8, it will jump in the packet list down to 8, select it, and then show us what it's talking about. So it says the dissector for OID not implemented. Contact Wireshark developers if you think you want this supported. So if we scroll down and look, we see that, okay, it's under the certificate management protocol, and it's under here under info type and value, and here's the error that it's talking about. We can also go down to packet 14, which looks like it has numerous problems. So we can click on packet 14. It automatically jumps us down. We can see that the sequence is expected, but there was a tag that was unexpected. Another example we can take a look at on the sample captures is if you search for X400, first one that we're going to use is X400 ping refuse. And if you open up this file, you can download and open that with Wireshark. And if we go into the expert info, you can see that there's a warning on packet 10. There's a connection reset. So we can click on that. It takes us to packet 10, and it highlights exactly what the problem is. In this section, we've gone over the basics of TCP/IP and how a packet is built, how to use the time information in a packet capture to your advantage, and how to add time columns and change the time settings, how to view different statistics in Wireshark on your packet capture to help get an idea of what the capture contains, and how to use the expert system, which is a nice hidden feature in Wireshark to show you exactly what problems are in the packet capture that Wireshark knows about. Our next section is going to be an introduction into analysis of different protocols. Welcome to Section 6, Introductory Analysis. In this section, we're going to take a look at DNS analysis, which is resolving domain addresses into IP addresses, ARP analysis, which is resolving IP addresses to MAC addresses, IPv4 and v6 analysis, and some ICMP analysis and how it's useful to you. Welcome to video of DNS analysis. In this video, we're going to take a look at how DNS works from a basic level and how do common issues with DNS look like in a Wireshark capture. What I'm going to do here first is flush my DNS cache on this computer, which will clear out any of the cached entries on this device so that if I try to resolve any of them, it will have to go get a new resolution from the servers out there on the internet. We can do that with ipconfig /flush DNS. Now that that's cleared out, let's do a standard resolution. Now that we've cleared things out, and before we do a resolution here, what DNS does is it resolves domain names and different records of those domain names to IP addresses. That's really its primary purpose here. It's used for all sorts of things. Browsing the internet in any sort of fashion, the World Wide Web, if you're trying to resolve FTP servers, game servers, trying to run Active Directory on a domain internal into a local network, trying to run VMware, all sorts of different services out there use DNS. And there's a common mantra in IT that even when you think it's not DNS, it's usually DNS whenever there's a problem. So let's take a look at what a normal DNS resolution looks like. So what we can do is type nslookup in Windows here. We'll do a space and select a domain to resolve. So we'll use wireshark.org, and I'm going to force this to go out to Google. 8.8.8.8 is the Google DNS server. So we're going to force that query to go out to Google directly. If I push enter, here we go. So in this result, you see that we have the server that responded to our query, 8.8.8.8, and that's its DNS name for that server address. And these are the answers that it has for that device, for that server. And you can see that we have both IPv6 and IPv4 addresses. The IPv6 addresses you can see have a very different format from IPv4. If you're unfamiliar with IPv6, take a look at other courses that are available from Pack Publishing regarding IPv6. So what we want to do is take a look at this from a packet level. So I'm going to flush my DNS cache again, and we're going to start a capture on my local interface. Now that that capture is running, let's go ahead and we'll do the same command as before. Do nslookup wireshark.org 8.8.8.8. Push enter, and we will stop this capture. So let's scroll down, and you can see there's a whole bunch of DNS here as well as some other protocols. So what we'll do is we'll use a filter, and to simply type in DNS in the display filter, that will get rid of any other junk that we don't want to see. And what we'll do is look down here. Here's my first request. So we have some other DNS requests that occurred by my system above here. We can ignore this one. And we're going to take a look at this first query here. You can see in this query, it's actually asking for 8.8.8.8. And so it's actually asking for the domain name of the domain server. And you can see it has a transaction ID of 1. If we look at the next query that happened, wireshark.org, you see that it has a transaction ID of 2. If we look at the packets in response to this query, they will have a matching transaction ID. We can see up here in packet 34, which is the response to the query on packet 33, that it also has the same transaction ID as the query. This is how you can match up the queries to the responses. And so a good example as to why this is useful is if you see a number of responses or queries even that are going around on your network and showing up in your packet capture with the same transaction ID over and over again, you may have a loop in your network. So that could point to a problem with spanning tree, for example. It's also just useful in general for us to be able to determine which ones are matched up from query to response. And you can see Wireshark, as you mentioned before in previous videos, automatically is showing us that here's a related packet between the two. And we also have a line here that tells us within the DNS section of the packet details that it's has a response on packet 34. And if we double click, it'll take us there. And then of course you can go back and forth between the two. So transaction ID is very useful. Let's go down to our second query for the actual wireshark.org, and let's open up the flags. We can see that there's a flag turned on here. We have a 1-bit enabled where it says recursion desired, do query recursively. This means that the query is requesting from the server that it ask other servers if it doesn't happen to know the answer to our query. So a DNS server could have additional pointers configured in it or additional forwarders set up on it to go look for the answer to a DNS query. So this query flag is saying, yes, please do that for us. So let's go down to packet 39 where my system requests from Google the wireshark.org A record. And we can see the response on packet 40. And we dig into the flags here and it says this is a response. Bit 1 is enabled, so this is a response message. It has recursion desired is enabled, sure, and recursion available, yes, I can do recursion. We scroll down and we see that we have answer RRs too. So we have 2 responses to this. Here's our query. And we'll go down to answers and we see that we have 2 records for wireshark.org. So it looks like wireshark.org is using some sort of load balancing system because we have an A record of 104.25.11.6 and 104.25.10.6. So if you go to wireshark.org, it will take you to either of these 2 addresses. You also see that there's a time to live value. We have a TTL of 169. And the 169 is the number of seconds that this record is to be kept on my system before it requests a new record. So the TTL value is very short here. And most likely this is something to do with the fact that they are using a load balancer. And if there's any sort of change in the address, it wants us to get an update as quickly as possible. So it doesn't want us to keep a cached version of bad IP addresses for a very long period of time. For example, many defaults are 8 hours or 24 hours. So converted to seconds, you might see 86,400 seconds or so. Let's take a look at a DNS request that will fail. What we'll do is we'll create some sort of random domain here, put in some gibberish.com, and I'm going to start a new capture. Go ahead and push enter. There's our answer, and we'll stop the capture. We can see we have the requests like before. We're looking for the 8888 domain name. We have a .home here, which we can skip past, and here's our actual request. And just like with Wireshark.org, you can see that we received, I don't know if you noticed this in the last one, we've received an A record as well as a quad A record. And that's because my system is requesting both IPv4 and IPv6. You saw that in the command line output when I did Wireshark.org. So we have an A record, which is the IPv4, and a quad A record, which is IPv6. But you see here that we have some sort of gibberish domain name, which obviously responded back in that command line saying that it couldn't find a result. So I sent out a query asking for 45yt blah blah blah.com, and I've received a response from the DNS servers at Google saying no such name. If we go up here and take a look, we have messages or response, no such name, reply code, no such name. And if you remember from the filtering videos, we can right click on this and we can apply a filter based on this selection. So what I just did there was I filtered our display filter based on no such name as the error code in DNS. This is a great filter you could apply if you're doing a packet capture where there's some sort of connectivity problem. You could look for failed DNS queries. In this video, you learned a little bit of basics on DNS and some DNS query examples. Next video is ARP analysis, where we'll be resolving some IP addresses to MAC addresses for layer 2. Welcome to video of ARP analysis. In this video, we're going to take a look at how ARP works, resolving addresses from IP to MAC address, and what do ARP issues look like in Wireshark. So what ARP does is it resolves IP addresses which are layer 3 addresses to MAC addresses which are layer 2 addresses. Addresses that are used on our local link, our local Ethernet bus. And we need that information in order to construct a frame which encapsulates a packet so we can send it onto the wire. So when a user or an application requests data from a specific IP address on layer 3, our system has to figure out what that MAC address is if it doesn't already have it in its cache. We can check what MAC addresses our system already knows about in its ARP cache. Just like DNS had a cache of locally known information, ARP is also locally cached. So what we can do is type in Windows ARP --A. If you push enter, you'll get a list of all of the known IP addresses in layer 3 matched up with the physical addresses, which is the MAC address on layer 2. And what you see here on the third column is it says type static. All of these addresses are addresses that my system knows about because they are coded into the operating system at this moment. So these addresses are multicast addresses that it knows about by default. It knows some VMware interface IP and MAC addresses. It knows a number of things that already exist. If we scroll up, we see that we have some dynamically learned addresses. So here's some statically known information, again some more multicast for this interface, whereas the other ones were a different interface. Here's my primary interface. We have my static information that's known for that interface, and we have dynamically learned addresses. These are all MAC addresses that have been discovered for specific IP addresses, and they are cached for a specific period of time. And then if I need to access that device again on layer 2, it will do an ARP request again. And so what we'll do is take a packet capture of a normal, good ARP request. I'm going to start my capture. and we're going to ping a known good address on IPv4. We see that we receive a number of replies. My system has sent 4 pings using ICMP to this device, and it all responded. Before it was able to do this, it had to figure out what the local physical address is of that device, what the MAC address was, before it could even do this first response, first request. We'll stop our capture, and let's do a filter for ARP. That way we only see our ARP traffic. And we're going to skip some of this information. There's some other devices here that are on my network that are also trying to do ARP requests. But if we look here, we have ASRock interface. There we go. That's my motherboard of the computer I'm using, who has 192.168.77.97. Tell this guy 77.159. That's the IP address of the system I'm using right now. We get a response saying 192.168.77.97 is at the following MAC address. This is a Netgear NAS device that I have on my network. If we go into the ARP information in the packet details pane, we can see the same information that's in summary form here. It's an Ethernet response. The sender MAC in this frame is from the Netgear. It's being sent from the Netgear's IPv4 address, and it's being sent to the initial requester, this guy, being sent to my system with the following IP. It's one thing to be careful with is if we look at the request where I did the ARP request, it was sent from my system at this MAC address and sent from my system at this IP address, but it was sent to 00000 because it didn't know who it was going to, but it did know the IP. So in the initial request, the ARP request, the sender is the device requesting, and then in the response, the sender is the device that's responding. So note that these kind of flip-flop. You also notice here in the ARP request, it's a broadcast. We can see that here where it says destination broadcast on Ethernet 2. It's going to a broadcast address. So when my system is trying to find on the local Ethernet bus the MAC address of the device that has the following IP on layer 3, it doesn't know who to talk to for that. So it sends out a broadcast to everybody. And then the device that happens to know that information receives it, because everybody got a copy, it then responds. And similarly with DNS, if you see a bunch of repeats here, especially response frames that are looping over and over again, they just keep showing up in your capture constantly, that could again point to a loop in your network. You shouldn't be seeing these over and over and over again. Let's take a look at an example where an ARP request fails. What we'll do is start a new capture, and this time I'm going to ping an address that does not exist on my network. We're going to see destination host unreachable show up. I'm going to do that a couple times. Since I'm trying a ping, it's going to do that 4 on a Windows system. If you're on Linux or Mac, it'll probably do that non-stop depending on what you use. Go ahead and stop that capture. We have plenty of information here. And we can see there's my request, who has 77.124. We can see that here. Here's the target. And we just keep requesting it over and over and over again. You can see even more down here. We're still requesting, still requesting, still requesting. We're trying to desperately find who has that MAC address for that IP, but it doesn't exist. And so it just keeps trying and trying, and it keeps timing out and failing, and that will show up in our results, as you saw in the command line, as an unreachable. In this video, you learned a little bit about ARP resolution, resolving an IP address to a physical MAC address on an Ethernet bus, for example. Next video is some IPv4 and v6 header analysis. Welcome to video IPv4 and 6 analysis. In this video, we're going to take a look at differences between IPv4 and IPv6, learn about issues and features such as fragmentation of these packets, broadcast storms, and the flags within the IPv4 and the IPv6 header. What we have here is some data from a packet capture going to a website which was encrypted. So that's why we see a lot of TLS here in the protocol information. And we have application data, which is all of the encrypted data transmitting back and forth to the web server. And what we're going to do is go to IPv4 here in the packet details, expand that, and we can take a look at the information in the IPv4 header. We can see here right off the bat that it's saying that it's version 4, otherwise it would show version 6. And it has the header length, the number of bytes in the header. Sometimes the header length can fluctuate, so it defines how big that header is so that the application knows where the differentiating point is between the header and the actual data in the packet. We also have some DSCP information for quality of service purposes and the total length of the packet. If you're familiar with MTU, such as setting the MTU of the interface of a router or a computer, that's where this comes into play. Total length is the total size of that packet. If the total size of a packet is too large, it will fragment. We see that here where it says fragment offset. And if we expand our flags, we can see that we have fragmentation settings in here in the flags. So we have more fragments are coming or don't fragment. The fragment offset tells the IP stack where to pick up with the additional data that's coming so that it can combine it into one large packet. We also have a TTL, which usually is at some sort of default number such as 24 or 60 or something like that. And as it hops between the different routers throughout the internet or your local network, wherever it happens to be destined to go, it will decrement 1 as it goes through each device. And if it reaches 1 when it's received on a router, if it's a TTL of 1, then that router will discard that packet. If a host machine receives a packet with a TTL of 1, it will process it because it doesn't have to actually route it somewhere. The TTL prevents packets from looping around forever throughout a network. So if it loops through 60 devices, it will then be discarded so it won't get stuck there forever. We also have a protocol definition. Is it a TCP packet, a UDP packet, some other type of protocol? And we have some checksum information to ensure that the header has not been manipulated in any way. Notice that it's not a checksum of the entire block of data, such as the FCS at the end of a frame, which encapsulates this, but it's the header checksum to make sure that the header itself is not manipulated. And then of course we have the source and destination addresses that we're coming from and going to. Let's take a look at a packet that's been fragmented. And we can actually see that here, a little bit below, we have an IPv4 packet, and it says fragmented IP protocol in Wireshark here. It knows that it's a fragmented packet. We see that it has a length of 1300 bytes, and in the flags, it has the 1 bit turned on for more fragments. So it says there's a fragment coming up. There's an additional packet. That next packet is part of this. Combine them. We see that the protocol is a UDP packet, and we see that it was generated with a TTL of 128. Since the source was my local machine and it's going out to the internet, I know that this is the generated TTL because it's being recorded and captured on the device that is sending it. So my system is actually defaulting the TTL to 128 here. The next packet is that continuation of the packet above. We can see that here where it says fragment offset. The fragment offset is 1280, so it knows to combine it with that previously captured packet. And you can see that down here, Wireshark actually combines them in this little information section here in the details. If we expand that, it says there's 2 packets involved here. We can select the first one and the second one. Here's our first. If we go back to the second, there's the second. So Wireshark is smart enough to know this. It takes a look at this header information and it provides these details for you so you don't have to do the math yourself. It even says here's how many fragmented packets there are within this one transmission and additional information such as the total length of the reassembled data. An application can define whether or not it's fragmented. So when an application wants to communicate it will tell the stack to set the don't fragment bit or not. Depending on the application and its requirements, it may say that it does not want its data to be fragmented. Maybe it's an encrypted packet, and if you fragment it, it will mess up the encryption. So it doesn't want to have that information fragmented, so it will turn this bit on so that the IP stacks know on both sides to not fragment the data. If you notice with this packet, the identification, the ID field on this initial packet that was sent that's going to be fragmented has an identification of 3C78. If we look at the second packet in this series, we see that its identification is also 3C78. Remember when I was talking about the ID field, it changes based on each conversation, each packet that's sent. If the identification is the same, that's an indicator that the packet is fragmented. That's how Wireshark is actually combining them and realizing they're part of a series, because the ID is the same. But the data within it is different. So it's not a duplicate, but it's a continuation of a fragmented piece of data. Now here in an IPv6 packet, you'll see that the header is somewhat similar to IPv4. It's actually a little bit simplified. It has a payload length. It tells you what kind of data is within it. Is it TCP or UDP? It has a TTL, they call it hop limit. And it has a source and destination address. Remember that the addresses look different in IPv6, it uses hexadecimal. In this video, you learned a little bit about IPv4 and 6 headers and the flags within that and fragmentation. In our next video, we're going to take a look at ICMP, why it's useful as network engineers, and some of the flags and information in an ICMP header. Welcome to video of ICMP analysis. In this video, we're going to take a look at how ICMP is useful as network engineers and what some of the different types of ICMP are and what they mean. The first thing I'm going to do is create some ICMP packets. What we'll do is create a ping request, which is a type of ICMP. So let's go ahead and start my capture. And we'll go ahead and ping Google again, 8.8.8.8. Each one of these replies is a series of ICMP requests and responses. Stop this capture, and we're going to apply an ICMP display filter. Here's all of my ICMP packets that have been sent and received, and we can see that we have a request, 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 and reply, 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 reply. That coincides with the 4 replies that we saw in the command line. So we see here we have reply, 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 and reply, 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 reply. If we dive into the header, we'll go down to the very bottom here in the packet details, ICMP, and we see we have type and code. Type and code are the 2 important parts within ICMP. We see here we have type 8 echo request. Then we have, in the next packet, type 0 echo reply. The type and the code give us information about what's going on in the network. Now this is a very simple example of requesting a poll of a device and a response from a device to see if it's alive. It's basically like ringing the doorbell of a device to see if it's there. But there's other types and codes within ICMP that are useful to our devices on our network and useful to us as engineers. So a very simple one is echo request and reply to see if something is accessible. If it's being allowed by the device, such as firewalls, they may be blocking it, but it's a very useful thing. We also have other types and codes we can look at. If you go to the ICMP page on Wikipedia, we can scroll down and take a look at all of those types and codes. And you can see here that there's a number of different types, and there's codes within each type. You can see here was type 8, echo request, used to ping, and type 0, echo reply. But we have these additional types that are here as well, such as type 3, destination unreachable. A router may send an ICMP packet back to a device, letting it know that it's unable to access a certain network or host for it. And you can see all the different types that it has available to describe to the requesting device why it can't reach the specific resource that it's trying to get to. Another common type is router advertisement and router solicitation. These allow hosts to request and receive a router to access a specific network. Additionally, we have type 11, time exceeded. Remember when I was talking about the TTL and how it starts at a certain number such as 60 or 128 or something like that? And it will then decrement as it goes through the different routers throughout a network and across the internet. When a router receives a packet with a TTL of 1, it will discard it, and at the same time it will generate an ICMP packet and send it back to the original source device, letting it know that the TTL was exceeded and that it needed to discard it. And it will do so with type 11, code 0. We can see an example of that here. These black ones that are highlighted by default in Wireshark all have time to live exceeded. So there are TTLs when they were out on the internet, ran out, they got stuck in a loop or something like that, and the router that discarded it sent back a message to me letting me know that my packets have been discarded. They did not make it to their destination. Now these are a little bit different in that they're fragments. We saw that the other one was code 0 and this is a code 1. But it's the same idea. It's sent back a type 11 to us to let us know that the TTL was exceeded for that packet. This is actually how traceroute works. It uses ICMP packets with different TTLs in order to figure out what routers are in the path from your source to a destination. Let's take a look at that. We're going to start a new capture, and I'm going to traceroute, and in Windows it's traceRT. I'm going to traceroute to a different device out there on the internet. We will traceroute out to our trusty Google DNS server. Why not? I push enter, and we see the path start to show up here. So you can see it has received a number of responses as it went through each different router. And then every once in a while you'll notice that it gets some timed out responses here. Depending on the router or firewalls that it goes through, they may not send back information to us, and they may drop that. So that's why sometimes you'll get gaps in your path. But you can see that it picks up again as it finds another router that responds to us at least. And we're still going through the internet, we're bouncing through routers, eventually getting to our destination. And if you noticed, each one of these hops was done 3 times. So it gives us an average of the response time for that specific router over an average of 3 attempts. And so it goes from router to router to router. If we take a look at this, we should see 3 requests for each router. And what it does is my system, when it creates a trace route, it starts out by sending a packet to my destination with a TTL of 1, not 128 or 60 or anything like that. It sends it to 1. So it's going to go to my router. My router is going to get it and say, I can't do anything with this. I need to discard it. The TTL is going to go to 0. And then my router sends a ICMP back to me, letting me know that my time to live has been exceeded. And what we can see is that's exactly what happens. I sent out a ping request, an echo request, with a TTL of 1. My router responded to say, sorry, I couldn't do it. Then I do it again for that second attempt. I get a response that says, nope, I can't do it. Third one, same thing again. Then it goes and creates one with a TTL of 2. So it gets through my router, because my router sees that it's a 2, it decrements it to 1 and forwards it. That's completely valid. Then it goes to the next router up the chain. On Verizon we saw. That router sees it. It sees that it's a TTL of 1. It has to discard it and send back a response saying, no, sorry, I couldn't do it. Your time to live has exceeded. I do it again. It responds. I do it again. It responds. Now we create a TTL of 3. And it keeps doing that. No, can't get there. Same thing, can't get there. Same thing, can't get there. And a TTL of 4, and so on. And so you get the idea here. That's how traceroute is able to map out the routers from point A to point B, because it uses the ICMP TTL exceeded errors in order to figure out that device, because it knows that the ICMP packet is generated by the router as a error code back to us. So luckily we can use that IP information to map out the hops that I go through in order to get to that destination. Very clever. In this section, you learned how DNS functions and some DNS analysis, how ARP works, resolving those MAC addresses, IPv4 and 6 headers, and how to take a look at some of the details within the headers, as well as ICMP, why it's useful to us as network engineers, and some information on how traceroute works and the headers in that as well. Our next section, we're going to start diving in more into analysis and start taking a look at some additional protocols and applications. Welcome to Section 7, Network Protocol Analysis. In this section, we're going to take a look at UDP analysis, the connectionless protocol, TCP analysis, the connection-oriented protocol, and graphing I/O rates and TCP trends, being able to visualize this data that we analyze. This is video 7.1, UDP analysis. In this video, we're going to take a look at how UDP works, what it is, and what's in the UDP header. The UDP protocol is a connectionless protocol, and it's very lightweight, very small header. If you'd like to learn more about the UDP protocol, take a look at RFC 768, available from the IETF. This is the original specification. It's been updated since, if you look through all of the RFCs, but the original specification is 768, and if you'd like to learn about all the details of UDP, which is relatively short, you can do so at this file. Let's take a look at UDP in Wireshark. Here I have a capture of just a few seconds of data, and here we see a whole mixture of applications and protocols. What we can do is simply filter based on UDP. If you push enter, now it only shows UDP packets. And you can see that we have some additional protocols listed in here that are applications that use UDP for their transfer, such as BJNP, which is used by the Canon printer that I have. What we can do in the packet details is take a look at the UDP section, and in the UDP header, there's very few fields. UDP always has 8 bytes in its header, and there's only 4 fields. We have a source port, a destination port, the length, which is the total length of the packet, including header and data, and a checksum, which validates the header information, but it does not encompass all of the data like you would expect with the FCS in a frame, at the end of a frame. And you can see here that we have an unverified checksum. By default, this option is not enabled in Wireshark. What you can do is go to your Edit Preferences, go to your Protocols, we'll skip down to UDP, and you see we have an option here for Validate the UDP checksum if possible. We'll turn that on, and you can see that it now says correct. So if there were any problems in the header and it was manipulated in transfer, we would be able to see that here and it would be marked. Then if you expand that, it'll tell you what the checksum information is that it was calculated. There's usually very few problems that you'll have with a UDP transfer. Either they work or they don't. They do not guarantee any connectivity, and the applications will perform any sort of retransmission if necessary built into the application. It's not handled within the stack like it is with TCP. Because it has a very small header and very few fields, there's very few options to be turned on and off. There's not much here. It's meant to be very simple and lightweight, which is great for voice over IP or streaming video, anything like that that is very time sensitive. It sends the data on its way and it hopes it gets there. Great if it does. If it doesn't, then oh well, you miss a packet or two. One thing you can do if you're not sure if a packet is UDP or not when looking through the packet list up top is we can create a column based on UDP here. So we right click on that and we apply as column. We have a new column now that says user datagram protocol, and yes, so it is a UDP packet. So if we remove our filter, we see that we now have yes and blank listed throughout our capture. That's a nice way of easily seeing what is a UDP packet and what isn't, depending on whether or not you have different coloring rules or something like that that's in a large packet capture. One of the few problems you may see with UDP are destination unreachable responses. Those are ICMP packets, if you remember, following UDP connection attempts. So if you have a UDP connection attempt and you receive an ICMP destination unreachable in the next packet, and you have a number of those continually occurring, that's an example where you may have some sort of connectivity issue that you need to investigate. And that's really the only sort of response you're going to get because UDP does not send responses. The device itself may send a response telling you that a network is unavailable or something like that, hence the destination unreachable. But otherwise, UDP itself is not going to tell you anything. And so that's why there's very few things that you will see in a packet capture regarding UDP issues, because there's nothing built into UDP to tell you there are issues. In our next video, TCP Analysis 1, we're going to take a look at all the different fields in the TCP header and the options that are available. Welcome to video 7.2, TCP Analysis 1. In this video, we're going to take a look at how TCP works, what's in the TCP header, and some of the flags and options. If you'd like to learn more about TCP, like I've mentioned with UDP, you can look at the RFC that's available from the IETF. You're looking for RFC 793, which is the original specification for TCP. And you can see here on this page, I've gone to a different section within IETF, which provides a little bit of an interactivity here. And you can click on the different RFCs that have updated the TCP specifications. And it also, if you scroll down, provides you a nice little table of contents. The RFC shows a little diagram of how the TCP header looks. We have source port, destination port, sequence number, acknowledgement number, data offset, some reserved bits, window size, header checksum, an urgent pointer, options, which is an expandable section. We have some padding, and then the actual data. If we go into Wireshark, we can see that. So let's go to a TCP packet. So we see we have some TLS traffic here that happens to be running over TCP. And again, just like I mentioned with UDP, we can right-click on that and apply it as a column, and you can see that yes, it is indeed using TCP. If we expand TCP, you'll see the fields that we were just looking at in the RFC. We have the source and destination ports. You can see this system here. My computer was accessing this web resource on port 443. And these fields here, which you've noticed in other packets that you've looked at most likely, anything with a square bracket is created by Wireshark. They are not actually fields within the header. So we can skip over those. We have the sequence number. We have an acknowledgement number. These are relative numbers, if you noticed. And I mentioned this before a little while back, that they started with 1 in this example. The actual raw number is not 1. Wireshark shows it as 1 and as a relative number to make it easier for you to look at. Otherwise, it's a very, very long number, and it's harder for humans to look at and diagnose. So we have a sequence number and acknowledgement number. We have a header length. Tells us how big is the header, because the header can change in size in TCP, unlike UDP. So we have to tell it how long is it. We have some flags. We have some congestion information. We have the urgent bit. We have an acknowledgement, push. We have reset and SYN and FIN. A lot of this stuff is going to look familiar, such as SYN and ACK and FIN, with creating a connection and finalizing a connection. We also have window size, which tells us how large of a chunk of data that we can transmit before having to do an acknowledgement. We have a checksum, which again is unverified, and an urgent pointer. If we want, again, like I mentioned with UDP, we can go into our preferences and go to protocols, TCP, and we can validate the TCP checksum if you would like. And we can see that we now have a correct checksum. Let's go ahead and create a new capture, and we'll take a look at a handshake creation and teardown of a connection. We'll start a new capture here, and I'm going to generate some traffic. Okay, so now we have some new traffic. I opened up a new web page and re-downloaded all the information for that RFC that I showed you from the IETF website. So what we'll do is we'll scroll down here and look for the beginning of our connection. Alright, this looks like the website that's being transmitted. It was over HTTPS, so seeing this TLS traffic is what I'm expecting. We'll right-click on this and follow our TCP stream. I don't really need this window here, so we'll just go back to our main packet list, and you see that the filter for tcp.stream equals 2 is listed here. So now this is our connection to the website for IETF. Remember I mentioned that TCP is connection oriented. It guarantees delivery of packets. So if you miss a packet, hence the acknowledgement system built in, then it will retransmit that. So what happens is we send a piece of data from the server to the requesting device. We send an acknowledgement that we received it. We send another packet, we send an acknowledgement that we received it. Sometimes, depending on the options and the functionality of the TCP stack in your network card and your drivers, you may allow for some enhanced features that have come out over the years, such as selective acknowledgements and some enhancements to allow you to be more efficient with the way of your using this acknowledgement system so that you don't have as much overhead. The creation of a TCP handshake we see here is a SYN, which says let's synchronize, let's create our connection. So we have a SYN here that is set. That's my system requesting from the IETF website to create a TCP connection. They respond back with a SYN and an acknowledgement. Then I, in turn, send back an acknowledgement as well. So we have a SYN, SYNAC, ACK, a three-way handshake with TCP. After that occurs, we then begin communications to retrieve HTTP traffic, which happens to be underlaid underneath TLS in this case. So we see the creation of the TLS connection here, some data being transmitted, key exchanges, and things like that. Then at the end of the communication, of sending and receiving whatever data that we wanted, such as the website being retrieved, my system will then finalize that and with an implicit method say, let's terminate this, there's no more data to be sent or received. We're going to end this TCP connection with a finalized statement here. And so what we do is in the flags we have a fin, finac, fin, finac. Sometimes at the end of this you'll also see a reset. So the finalize method using fin is implicit, saying this connection should be terminated, there's nothing else to be transmitted, but it's not explicitly told to remove the connection. So the system on either end may end up leaving this connection live. It's up to them. If you see a reset at the end of a connection after the fins, then that's an explicit way of one of the devices saying, yes, terminate this. This is an explicit way of saying, kill the connection, reset it, nullify it. If you see a reset before the fins, then that may be an indicator of a problem in the connection where the server or the requesting device, whatever it may be, saw a problem and reset the connection to try again. Now we also have options, which are an extension in the header to allow us to expand upon the abilities of TCP. And what we can do is filter on options, because if you notice, looking through the header here, we don't see anything that says options. So if we want to find anything that has options, we need to filter on that. What we can do in the display filter is say tcp.options, and now we're showing all the traffic that has options enabled in the header. So if we scroll down in the details area here, we have a bunch of information about the options. We can skip the no-op stuff, and we want to look at the things that are more interesting to us, such as TCP SAC and window scale. This packet, for example, has TCP SAC. SAC is an acronym for Selective Acknowledgement. Selective Acknowledgement allows you to acknowledge traffic while still requesting for missing traffic without having to have the entire block of packets resent to you. So if you're having, let's say, 5 packets at a time being sent to you before you send an acknowledgement, and one of those is missed, without selective acknowledgements, all 5 would have to be retransmitted to you. So the farther apart the acknowledgements are between the number of packets that are sent to you, the more efficient it is, because you're not wasting all this bandwidth with overhead acknowledgement packets. But if you run into a problem, then more data has to be retransmitted. Selective acknowledgements is a way of getting the best of both worlds so that you can have a large block of packets being sent to you without having to acknowledge them every single time. But if you miss one, you can then request just the one to be resent to you. You can still acknowledge all the other packets. So if you see TCP selective acknowledgements, that means that the two devices have allowed for selective acknowledgements and they've agreed upon that. Both sides will have to allow for that feature set to be enabled in order to utilize it. We also have window scale. Window scale allows us to go beyond the initial window size. The initial window size was at a maximum of 65,535 bytes, which isn't a lot anymore, so we want more than that. We can do that by using window scale. Window scale allows us to multiply the window size by a factor. So you could say 65,535 times whatever the window scale is, for example, and that you could get a very, very large window size in order to most efficiently use your bandwidth. In our next video, TCP Analysis 2, we're going to go into detail of some of the different things you can do to analyze TCP packets now that we've taken a look at the header information and really dive into what's occurring within a TCP connection. Welcome to video 7.3, TCP Analysis 2. In this video, we're going to take a look at filtering on many different TCP header fields and what kind of issues we could see based on some of those fields that we look at. So what we have here is a packet capture of two websites that were opened. And you can see I still have my TCP column enabled, so we can go down and find a TCP packet. And we'll see the field information again. And like with many of the other protocols that we've looked at, we can right-click on any of these fields that are in here and apply them as a filter. What we may want to do is expand the flags here and look for anything that has the urgent bit set. The urgent bit is not often used. The only one that I can think of is using Telnet. And what it does is it prioritizes the packets, basically. So what we can do is right-click on that urgent bit and we'll apply a filter. And we'll see that the filter is created, but it's based on 0. So we're going to change it to a 1 and see if there's any packets that have the urgent bit set. And we see that there's none. So that's good. Another thing we can do is delete the filter back to tcp.flags. And if we press enter on that, it now is filtering based on every single packet that has flags enabled. And as you can see, we have a lot of packets that have flags enabled. So that in this packet capture may not be very useful. Depending on the type of traffic that you are seeing, that may be helpful to see what has flags and what doesn't. Here, it has too many packets that have flags to make that a useful filter. What we could do though is customize that and look for anything that has reset. Usually a reset is either at the end of a good connection as explained, or it's indicative of a failure. And what we'll do is we'll change our display filter so that it is tcp.flags.reset equals 1. And with that you can see we have quite a few packets that have resets. So what we can do is we can take a look at one of these and look at the traffic surrounding the reset to see if that's indicative of a problem. So let's choose this one and we're going to right click and follow TCP stream. Actually, you can see here that it's some sort of Google traffic. Close this. And we see, it looks like some sort of a certificate transfer here. We have a three-way handshake. We have a client and server hello. Looks like it was a TLS negotiation. And, okay, then we ended up completing our application data. There were some packets of application data. And then my system, this is my computer, sent a FIN-ACK. So we finalized the connection. That's an implicit termination. And then it was followed up with an explicit termination, the reset. So this is actually okay. So my system said I'm done with this connection, and then we're going to reset and totally terminate this connection. So that's actually fine. But you can see how that's useful to be able to pull out everything that is a reset. What we could also do is take a look at window size. And we'll do that with TCP dot window size, and let's do less than 50. Push enter, and we see here that we have quite a number of packets that have a window size of less than 50. Now you can see we have a number of packets here that have a window size less than 50. Usually a small window size is an indication of a problem. On a reset packet, not necessarily a problem because we're terminating a connection anyway, but if you see window sizes that are of a small value on standard data transfer packets, that's a problem. That's some sort of buffer problem in your one of your devices in the network stack on one of the two. Additionally, Wireshark has some analysis filters that we can use, and we'll show one that is window size related. We're going to do tcp.analysis.0window. If we push enter on that, you'll see this is actually all of the packets that have a window size of 0, which I've told you is a problem. So these are potential issues. These are acknowledgments from my system to a variety of different servers out there, with my system declaring that it has no buffer space available, its receive buffer is full, and it sends a 0 window response back to the servers out there saying please slow down. So this is a potential issue on my system right here. Another interesting one that we could do is take a look at the header length. Remember I said that the TCP header can fluctuate in size? Let's right click on header length and we'll prepare a filter with this selected. Notice how I didn't use apply, that way it doesn't apply it right away. And we're going to say anything greater than 20. So TCP header length greater than 20. And there we go. You can see that first one that pops up has 24. We have 32. Bunch of different packets here. Looks like most of them are 32. And so here's a good example of finding packets that have options in them. So if we scroll down, I know that the header length is larger than the standard 20 because it has options built into it somewhere. And here you can see this packet has selective acknowledgements and window scaling. You could also do a similar thing by filtering on options. So let's select that. We'll prepare a filter, and we're actually going to delete all that and just have it tcp.options. So here's every packet with options that are enabled within them. In our next video, graph I/O rates and TCP trends, we're going to now take what we've learned and apply that and create graphs out of these. Welcome to video 7.4, Graph I/O rates and TCP trends. In this video, we're going to take a look at using graphs to help visualize packets and trends, especially in TCP communications. Here we have a packet capture of a file transfer that has gone horribly wrong. As you can see as I scroll down here, we have all sorts of black bars coming up, which is a very telltale sign in Wireshark that there's something amiss. And if we scroll up here, you can see there's a striping pattern that comes about. That's a very telltale sign that there's a bunch of retransmissions. So what we're going to do is use this as our basis for graphing and being able to pick out some issues. One of the first things we'll do is go up to Statistics and go to TCP Stream Graphs and check the throughput. Click on that. And when a graph comes up, whether it's graphing I/O rates going into that section, going here through TCP stream graphs, or anything anywhere like that, all the graphs are unidirectional. So if we, depending on what packet we have selected, it will show us the throughput for that, or show us the I/O rate, or whatever might be that we are graphing. It's going to be for that one unidirectional transfer. So we see we're going from 1.64 to this public address. We're trying to pull HTTP. If you don't see anything in the graph, if it looks not quite what you're looking for, it doesn't seem like something's correct, click on the switch direction button. That'll provide us the opposite direction. So we see here now we're getting the throughput from this public address with port 80, the server, and it's going to our private address here, which was web browser. And we see that we have the throughput graphed here. We have the segment length, see if that changed at all. and we have the throughput itself in bits per second. And what you can do is, in the latest version of Wireshark, you can drag the graph around in order to be able to view it more effectively, or you can use your scroll wheel to zoom in, or you can use the plus or minus on the right side of your keyboard in the keypad area. You can use plus or minus. I like to use the scroll wheel just because it's handy, and almost every mouse has that. Also note that you can change the stream that you're following. So we can, if there were multiple streams that we wanted to look at, we could change the stream number that we're in. We'll leave it on 0 for this. Another nice feature with the graphs in Wireshark here is we can click on any point in the graph and it will take us to that packet. So let's we see a little gap here in our throughput. Let's click on that and we can see Wireshark brought us to that section of packets. And if you noticed when we went to statistics TCP stream graphs, there were several to choose from. In the lower left here, you can select between those types. You don't have to close this window and go back to the statistics window and open it again. We can switch between them easily here by simply selecting whatever type you want. So let's go to time sequence. You see here that we have a nice diagonal line in our time sequence. What that's showing us is the sequence number continually incrementing from packet to packet. Sometimes you can view issues in your packet capture with sequence numbers by seeing a drop in sequence numbers, or maybe a flat line where it does not increment upwards in the y-axis and it just continues on the x-axis. If you see anything other than a diagonal line, that's indicative of issues in your packet capture. So what we see here is this looks relatively good. We can close this. Now let's go to statistics IO graph. Now IO graph is a very powerful feature in Wireshark. And what it's doing by default is it's showing us all the packets per second. And all of this is customizable. You can change the interval. You can change whether it's linear or logarithmic scale. Depending on the needs of the packet capture that you're looking at, maybe there's very drastic differences between some different streams that you're wanting to graph, or maybe some differences between the filters that we want to apply, because you can layer filters in this section. You may want to use logarithmic for that. It all depends on the needs of what the packet capture looks like. But by default, when you open it up, Wireshark will show you the number of packets per second, and then every tick is 1 second. What we have are a number of additional layers below that that we can customize. And you see here that we have a name, so you can name the layer. We have a display filter. We have a color, so you can change the color. The style type, whether it's a line graph or a bar graph or something like that. You can change what the y-axis represents. You can turn on smoothing. You can do a number of different adjustments here to your IO graph to make it as customized as you need. One powerful thing to look for in a packet capture that you know has a problematic transfer are TCP analysis flags. So what we'll do is we'll do that for this second layer here. We're going to create a display filter for TCP analysis flags and layer that onto our IO graph. So what we'll do is double click on display filter, and it allows us to enter a display filter, and it will work just like as if you were adjusting the display filter in the main packet list area. So we'll say tcp.analysis.flags. Now if we apply this, it will create a second layer on this graph with a red line graph of any packet that has an analysis done to the flags. So whether or not Wireshark looked into the flags and it saw that something occurred and it provided some sort of insight into it, just like we saw with the expert info in the lower left. This display filter uses the same functionality as the expert info. What we don't want to include though are window updates, because window updates are good. As long as it's not a zero window situation where the window size is 0 and our buffers are full, we don't want to include all the packets that have window updates, because window updates are fine. So what we'll do is we're going to negate window updates from this. So we're going to do space, ampersand, ampersand. to say and tcp.analysis.flags and the following. If we use an exclamation mark, that will negate whatever we are about to include. So it will say not. So tcp.analysis.flags and not tcp.analysis.window update. So we're going to do tcp.analysis.window update. And you can of course click on these as well. When you're done, simply click away and it will apply the filter. Now you see we have the check marks on the left. That will enable or disable the following layers. So if we disable the top one, that gets rid of our packets per second. If we enable the second one, that will show us all of our TCP analysis flag issues. So we see here that there's a number of problems. What we can do is make this easier to view and really make it stand out, especially if there's a lot of data going on here. If we have a lot of additional layers, sometimes you may want to make certain layers stand out. What we can do is change the style of this to a bar. If we change it to a bar, you'll see that it's a bit thicker and it stands out more. And if you zoom in, you'll actually be able to see the red there. And it really sticks out like a sore thumb. And well, what we can do, as mentioned, is anywhere along this line, we can click on, and it will take us to the problem. You see here, here's all of our TCP analysis issues. So what we can do is click on that and validate this as well. If we click on one of these black ones, and we expand TCP, and we look at the analysis section, we see here that it's telling us that there's a duplicate. This is a duplicate to a previous acknowledgement, which is obviously a problem. That's indicative of an issue. Also note that these different layers are on top of each other. So that the top layer is the one that's closest to the foreground, and then the one towards the bottom is towards the background. And so if you have a lot of data on a foreground layer, it may overlap and overwrite visually what's going on in a background layer. So be aware of that. So for example, if we were to change the style of this to a bar chart, you'll see that that makes the second layer that we created with the analysis flags useless because it now is dominating the entire view. So be very careful with the way you change and use your different layers. In this section, you learned about the UDP protocol and its connectionless abilities, the very small header that it has. We also looked at TCP, the connection-oriented protocol, guaranteeing transmission of certain data. We looked at the header and learned about the fact that it has different flags and different options to expand upon its capabilities. And we also learned about the graphing functionality in Wireshark and the fact that you can add multiple layers and change the way that the lines and bar charts work in order to get a most useful graph as possible out of it. Our next section is Application Protocol Analysis 1. We're going to look at HTTP and FTP and some of the common applications that you'll run across on a day-to-day basis. Welcome to Section 8, Application Protocol Analysis 1. In this section, we're going to take a look at DHCP analysis. We're going to investigate how a computer gets an IP address as well as other fields and data. HTTP analysis, which we use every day browsing the internet, very common thing to have to investigate, and FTP analysis, including the different secure versions of FTP. This is video 8.1, DHCP analysis. In this video, we're going to take a look at how DHCP works, some of the fields that are within the DHCP protocol, watch a client retrieve an IP address, and really take a look at what happens with DHCP when a client requests for an address and receives responses. So as usual, let's start a packet capture. And what I'm going to do is release the address on my computer here and then renew it. What we can do is with ipconfig/release on a Windows computer, we can release our address, and then if we do ipconfig/renew, it will get us a new address. Now if we take a look at ipconfig/all, we should be able to see our address is assigned. Very good. And we'll stop our capture. And of course, with our big packet capture here, we're going to want to only pick out the DHCP traffic. So you would assume you could go up to the display filter and type DHCP, just like we've done for the other protocols, and just push enter and it works. But we see that there's a red bar up there. DHCP is not valid. Now why is that? Because the display filter is actually bootp. DHCP is based off of bootp. Bootp was the predecessor protocol to DHCP. So in Wireshark, they use the predecessor's protocol's filter. So you want to use bootp. So if we use bootp, we'll see that we have our DHCP release and discover. So this first packet here is the release. So my system already had an IP address and it wanted to get rid of it. So it sent a packet to the DHCP server, which is 77.1 here, and it said, please get rid of my address. And if we look into our DHCP details here, you see it says Bootstrap protocol. That's where bootp comes from. And we scroll down to the bottom, you see options. And if you look at option 53, it says we have a release. So that's where it's requesting to get rid of its address. The system then at that point has no address, and the local client erases the IP address from its information on the network interface card. Then after that, I initiated the DHCP renew command, which told it to go get an address. Now I did this because my system had already been up and had already retrieved a DHCP address on boot before I did my video capture. Commonly, a system will retrieve IP information and other configuration options from a DHCP server on boot of the operating system. But since my system had already had an address, I had to get rid of it and then forcibly tell it to get a new one with that /renew command. When a system requests for an address, it initiates with a discover request. And you can see that the discover, which down here we have option 53, discover, it sent it out to a broadcast, all 255s. That's because the client doesn't have an IP address. You see it has 0000 as its source. It doesn't know where it needs to go talk to the DHCP server. So it sends it out to a broadcast address, hoping that anybody will respond to its request for a DHCP server. And so what that is the discover packet is asking for a DHCP server. It says, I'm trying to discover a server. If you have multiple servers on a subnet, you may get a different server offering itself from time to time. That can cause problems sometimes depending on your network design. If you have a simple network, such as a home network, and you have two DHCP servers, most likely one of those is by accident. And you can have that problem when people bring in home wireless routers or something like that into a workplace and they don't turn off the DHCP server. It can cause problems like this. So looking for offer packets sometimes is useful in packet captures because you may not necessarily want to see them. That may be a bad thing. If you happen to see offers from a server address that doesn't make any sense according to your network design, then that's a red flag. And you can, of course, right-click on the offer and select that as a filter so that you can filter all of your packet captures based off of just the offer. You see that we've only pulled out the offers here. So if we had a whole bunch of offers from a bunch of different servers, that could be a problem. If we go back to our standard bootp filter, you'll see after the offer where the server is now responding to our broadcast that says, yes, I am a DHCP server, you can use me. I then send out from my client a request. And you can see down here in the options that I'm actually requesting a specific address. Now this you would not normally see on a new system that just booted up. But because my system here, the client, already knew that it had a previous address, it kept that information saved even though it was not configured in the network card. It requested that specific address to renew it and put it back into its configuration. You can see that it also knows now the server. So it sends it out to the server, but it doesn't come from a layer 3 IPv4 address here because it doesn't have one yet. It's requesting it. So it still sends it out to the broadcast, but it says, hey, server 77.1, please give me 77.160. And the server then says, yes, I acknowledge you. And by the way, it's okay. You're allowed to use that IP address, as well as here's some additional information. So you're using the 77.1 DHCP server. Oh, and by the way, here's how long your lease time is. It's good for 1 day. That can be customized. Here's your subnet mask. Here's the domain name, if applicable. Here's the router, which is your default gateway. And here are some DNS servers that you can use. And you may see additional options in here. These option numbers reflect a whole bunch of different things that you can configure in DHCP. It's not just for IP addresses. You'll see this commonly used with voice over IP phones because you can pass different options such as option 43. You actually tell it what VLAN it needs to belong to and force it to the other VLAN. And then you can also tell it where the TFTP server is to retrieve firmware information, all sorts of different things that you can send to a device to automatically configure it. That's why they call it the Dynamic Host Configuration Protocol. It's not just for IP. If you want to learn more about it, you can, of course, take a look at the RFC. The RFC for DHCP, remember this is the upgraded version of BootP, is 2131. And you see it's quite a lengthy document. There's quite a bit in here. And it goes through a lot of the functionality of DHCP. Now, it will not include every single option and every single thing that you can configure because some of them are vendor specific. And of course, DHCP has been extended since 1997 with additional added on features. Then our next two packets, we see DHCP inform, and these are requests from my client. Now that it has its layer 3 IPv4 address, it's now requesting from the server additional parameters. And you can see them listed down here. Here's the additional parameters it wants. It's looking for static routes, any NetBIOS information, any additional vendor-specific information, that option 43 I was talking about. Anything like that, it's requesting from the server, and if it happens to have it, then the server would respond and say, yes, by the way, I have the following additional information for you. And so that's the basics of DHCP. It's a very simple protocol, a little bit more complex than DNS, but still relatively simple, very useful. There is a IPv6 version of DHCP, and as well as many other ways of addressing IPv6 hosts. Up next, we're going to take a look at HTTP in HTTP Analysis 1. Welcome to video 8.2, HTTP Analysis 1. In this video, we're going to take a look at how HTTP works, what some of the codes are that are within HTTP, what's inside a packet, the source and destination information, and some of the options that are in there, and how servers and clients interact and show a connection between a server and a client. What we'll do is start another packet capture and open up a website. And so in this example, I opened up a web page to npr.org, which happens to be an unencrypted website. It uses plain HTTP by default. So that way the communications are not hidden behind TLS encryption. So we can take a look at what actually happens within the HTTP headers. So let's scroll down here and we see we have the npr.org DNS resolution. And here's our answer. And the beginning of the SYNAC three-way handshake for the TCP connection. We also see some Akamai DNS resolutions as well. And that's because if we take a look at the npr.org here, it actually is hosted off of some Akamai servers, which is a content distribution network that's distributed around the world, so very quick to respond. And so it has to resolve some of these additional servers as we go along. But we can see here I have an initial TCP request to the actual server. And then my system here asks for section/news, because I was opening up the news section on npr.org. And if we scroll down, we'll see, okay, well, there's HTTP protocol, and here's some TCP reassembled segment stuff. And it's a lot of TCP, and I'm not seeing anything for HTTP. What's going on? It's because we have the reassembly enabled in the options. This is something you'll probably want to turn off if you're doing HTTP analysis. Go into your preferences, go to protocols, go to TCP, and turn off Allow Subdissector to Reassemble TCP Streams. And if you turn that off, you see that we now get some insight into HTTP, and it actually shows up here in the info what the commands are back and forth for the HTTP traffic. And you can see they show up now properly as HTTP in the protocol column, and it says it's a continuation of HTTP as it transmits all of the website information from the server to my client. You can see the window size in use here actually as well. We have our nice big window size, and then we have packet, 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 acknowledge. Packet, 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 acknowledge. So remember when I was referring back to the window size and how it doesn't require an acknowledgement for every single packet? Here's a good example of it. And so if we take a look at the HTTP here, my system, 77160, did a GET request. And HTTP has two primary commands that we use, GET and POST. And so a GET request retrieves information, POST sends information. So you know how in some forms and such on certain websites, or if you make changes to a web settings in a profile or something like that, you'll be sending data to the server telling it to change something on the server. You do that with a POST. With GET, we are asking for information. So in this example, I am getting /sections/news, and I'm requesting it over version HTTP 1.1. There is a new version of HTTP which has recently begun to be used, and it's based off of Google's Speedy protocol that they had previously created. If you want to learn more about the Speedy protocol and what it was, you can take a look at that on Wikipedia or on chromium.org. They have a page on that as well. And it was really an experimental protocol to speed up traffic. And it has since been deprecated in favor of HTTP 2.0, which has now become the standard. So the ideas within Speedy have been merged into the HTTP 2.0 standard. And what it did was it basically optimized the HTTP header information and the communications so that it could achieve up to a 50% speed increase on a loading of a website. So it's very powerful and impressive. So when you see these GET requests, you'll be most likely seeing 1.1. Some really old clients, for if you're using like a really old program on a very old system, may be asking for 1.0. But you may see now 2.0 requests. Probably about a third of the major websites out there now use HTTP 2.0, and it will of course only increase over time. So we are asking for /sections/news, and then it's insinuated there that we are asking for the index.html page from in that. So we're asking for a folder structure. By default, HTTP will look for index.html or a couple other different files, index.htm or some other file format. It's based on the server to serve up that core page that'll first show up. And so from the server, we see we have a TCP acknowledgement to that GET request. And then the server responds back with, okay, that sounds good. I will send that to you because I've been able to find that page. So if you request a page that's incorrect, you'll get an error message. And in HTTP, we have different types of commands with different numbers. And if you'd like to learn about HTTP in more depth, of course, take a look at the RFC on the IETF website. You're looking for number 2616. And that's for 1.1. So remember I said there's a new one, 2.0, coming out. So of course that's going to have a higher number. And so when you look through the standard here, you'll see a bunch of different codes. Down here you see a bunch of the codes that are available. And of course there's details as to each code within it, but if you look on the left here, we have a status code number. And anything that is 200 or 300 are okay. So a 200 OK means I found the file, no problem. 201 says okay, I created it. 202 is an accept. These are all good things. If you get to 300s, there might be a redirects or a move file somewhere else. A 400 or a 500 is an error. So a 400 is a server error. Somewhere in the 400s are all server errors saying I can't find the file, you're not allowed to get there, it's forbidden, your method is not allowed, the server's rejecting your request. A 500 error is a client error, so there's a problem on your client side. So this is very common to see a 404 error when you try to request a web page that does not exist. It's a very common thing, and you see it all over the internet now, everyone's used to it. But a 404 error is, I cannot find the file. The server says, I don't know what you're requesting for, it's not where you say it is, I'm sorry, and it sends back a 404 error. Here we have a 200 status code, so everything is good. If we look in here into the HTTP header information, you see that we have a server Apache that may say something such as Nginx or some other server that's running. Apache is the most common one still. It'll tell you what it's running, if it's running PHP of different versions or running Python or something like that. It'll tell you what the content type is. Is it an HTML page? Is it some other kind of content type? Is it an XML page? Something like that. Sometimes you can have encoding as well. Some pages, some servers, allow for compression. So they'll compress with gzip, which is like creating a zip file of the server page that it's sending back, so that it is smaller and so uses less packets and is quicker to send to the client. It takes a little bit of processing power on the server and the client sides to do that, but it's usually beneficial. It'll also tell us how long the content length is. You notice that now when we've gone through all these different protocols, they almost always tell you how long the content is so that you can validate whether you've received everything. We also have an expires here and a cache control. This tells the system how long to save a page. So when your client receives the page, it will cache it for a period of time based on this, so that it can refer to its local cache if it goes back there again. So if you're constantly going back to the same web page all the time, it will load it off of your local cache rather than constantly pull the server for it and use up unnecessary bandwidth and resources on the server. If you wish to not use the cache, that's when you refresh a page, you can usually hold Control and then push the refresh, or Control F5 if you're a keyboard person, and it will force the cache in your browser to delete that page and request a new one. If we expand this section down here, line-based text data, it will actually show us the web page itself as it's sent to us. So here's the actual HTML tags. Doc type HTML, there's the beginning HTML tag to create the page, here's the header information, then throws in some JavaScript that they use, and so on. Our next video, HTTP Analysis 2, we're going to dive into HTTP a little bit more, talk about some more problems, and take a look at how you can decrypt TLS encrypted HTTP data, HTTPS, how you can decrypt that in Wireshark. Welcome to video 8.3, HTTP Analysis 2. In this video, we're going to take a look at investigating some issues with HTTP, looking at those error messages again, and how to decrypt HTTPS, which is TLS now, traffic. This also works for SSL. What we're going to do is download an example capture from the sample captures section on the Wireshark wiki. So if you go to this sample captures page that you've seen before, we're going to go down to specific protocols and protocol families and go to HTTP. Click on that. We'll have a list of some basic HTTP captures that we can look at. At the bottom here, it has a link to SSL with decryption keys. And we're going to download this top link, Snake Oil 2, tar.gz, the TGZ file. And what you'll need to do is extract that then with 7-zip or some other application, WinRAR, whatever it is that you use on your system, and extract that so that you can get to the files within. By default, Windows can only extract .zip files, so you'll need to download something like 7-zip or WinRAR or something like that in order to open it. When you open the cap file, you'll see that it's an older file. This is actually from somewhere around 2007 probably. So it's not a pcap.ng file, but that's okay. It still opens up just fine in Wireshark. And if we look at this, we see that we have a SYN, ACK for TCP, so there's our three-way handshake. We can ignore the source and destination. They've been cleaned up, so they're anonymous now. But we see we have a SYN, ACK, three-way handshake, and then we have an SSL, client hello, an acknowledgement from the server, then the server hello, acknowledgement. We start exchanging some key information for creating the SSL encryption. We share the cipher information, and we begin actually encrypting the data after that. And we see we have here encrypted handshake and encrypted data and stuff like that. So we have this data that's in here that's encrypted. We can't get to it. We have all this application data down here you can see. And all the application data is unreadable to us. If we expand any of this in SSL, and that's all we see. It's just gibberish. So how do we see the HTTP within it? We need to decrypt it. And with Wireshark, you can decrypt SSL or TLS traffic. You would need, though, the private key from the server. So if you do not have access to the web server, you cannot do this. This is great if you're on a corporate network and someone's accessing a corporate resource that happens to be encrypted and you want to decrypt it. Well, then you have access to the server so you can retrieve the private key. If you want to do this over the internet, you have to get the private key from whoever's hosting it. So in order to set this up, we're going to go to Edit Preferences, and we're going to open Protocols again, and we're going to go down to SSL. And you'll notice that TLS is not listed in here. It falls under the SSL, because TLS came about after SSL was built off of SSL. It all falls under the SSL protocol section here. So we're going to configure our RSA keys, those private keys, within the SSL protocol list, even if it is TLS that you're using. So what we'll do is click on Edit and the plus sign to add a new decryption key. What we'll do is add the IP address of our server. In this example, it was sanitized to 127.0.0.1, which is the local host. It's just a loopback address. We're going to define it as port 443 because we know this is HTTPS traffic that's using standard port 443. And we know that it's HTTP traffic that's behind it. And then we're going to double click on the key file section and select our key. So you see in that extracted file we have the cap file, a readme, and the key file. We're going to select the key file and then click OK. Once we click OK again, you'll see that the data has decrypted itself. So we no longer have all of these TLS protocol listings. It doesn't say application data. It actually shows us HTTP traffic now. We've now decrypted this. We still have the SSL protocol stuff up here because that's actually SSL traffic. It's doing the handshake and exchanging the cipher information so it can encrypt. That's okay. The stuff below is what we cared about. So now we can actually do our display filter for HTTP, and we can filter out just the HTTP communications. And we can see we have a few problems in this packet capture. So we have a GET request. Remember we talked about that. We're retrieving something. We were looking for a specific resource. It was responded from the server saying, okay, I found that file. They then tried to get two more images over HTTP. They were downloading some images. Looks like the Debian logo and something else. And then there was a response from the server stating that the resource was not found. There's that 404 message that I was talking about. So if we go in here, we can see 404. You also see that it says expert info here. Remember about that expert info. Go down to the bottom left, click on that, and it will provide you all of the errors that are in this packet capture. Don't forget about that feature. It pulls out HTTP errors. It pulls out anything that's of use. We then have a response that the images were okay to send. It found those resources and transferred that. And then it had some problems retrieving another file and another file. And then there's a 301 code where something was moved permanently. There's a pointer saying, oh, okay, this file is still around, but it's over here instead. So you can see there's a number of issues in this packet capture, but we can see that now thanks to our ability to decrypt the traffic. So in this video, we went over how to decrypt HTTPS traffic, whether it's SSL or TLS. And we also took a look at some of those error messages that I was talking about and the status codes of HTTP. We saw a 404 and a 301. So you can see how you can filter on those, and you know where to look within the HTTP packet detail information in order to pull out what you want with your display filter that you end up crafting. Up next, we're going to take a look at FTP analysis, where we'll investigate FTP, FTP active, passive, SFTP, FTPS, all the different flavors of it. Welcome to video 8.4, FTP analysis. In this video, we're going to take a look at how FTP works, the differences between the active mode and the passive mode, and how to transfer files securely with FTPS and SFTP. So what we'll do is start a capture once again, and I'm going to connect to an FTP server that does not use encryption. So this server here is a Belarus hosted server that has some Linux ISOs on it, and it allows anonymous connections. So I'm going to just log in with anonymous here, and we're going to use port 21 and click quick connect. We see that we've logged in. It states that it does not use TLS, and it listed the root directory. And we can see we have Debian listed here and Ubuntu and stuff like that. What we'll do is stop that capture, and if we scroll down through this, we'll see that we have a bunch of other types of traffic here, but then we see some FTP listed. So what we can do is create a filter with simply FTP in that, and that'll show us all the FTP traffic. And so here we see the connection over unencrypted FTP. You can see all the commands just like with HTTP. If we dig into our FTP section here, we see that we have very few commands that are transferred. We connected with our three-way handshake in the packets prior to packet 101 here. So packets 98, 99, and 100 were the TCP handshake. And then it states code 220, service ready for new user. So the server says, okay, I see you've created a connection to me. Let's send me some authentication. My software asked if it is capable of using TLS, which is the encryption that we use for HTTPS to allow for encryption. The server responded saying, no, I can't do that. Please just log in with the username and password. And then my software, the FileZilla client, said, well, what about SSL? And then the server replied and said, no, sorry, I don't do that. Username and password. And so then my client finally sent it a user saying, all right, here's the user command. I'm going to log in with anonymous. The server accepted that and said, please specify password. I provided the password with the pass command. The server evaluated that and it determined that those credentials were good, and it said login successful, code 230. My system then asked what kind of system type it is, what the server's running, and the server responded that it's using a Unix type server. It then asked for what feature set that it has available, and the server responds back with a list of features that it's capable of supporting. And you can see some of them in here, such as UTF-8 for extended characters, depending on what language that you might be using on your computer. So it supports a number of useful features here. Then says, okay, this is the end of my list. My client turned on the UTF-8 option. Server said, okay, no problem. Then my client requested print working directory, PWD. And the server said, you are in the root, the slash directory. That's the first directory that you're in. My client changed to binary mode, which is type I. The server responded saying, okay, no problem. I then requested passive mode. That was another feature that it was capable of providing. Passive mode allows FTP to communicate and transfer its data over a random dynamic port. So if you were looking at the port numbers here, I'm talking to the server, my client, which is running locally. The client software is running on 52.284. It's talking to the server on port 21. The data, these are just commands. The data itself has to go over another port. With FTP active, the data would transfer over port 20 and all the commands over 21. This is not a common thing to see nowadays because active mode can easily be hacked. It's not a very secure method because you know exactly what port that the data is going to be transferred over. So if you're in the middle, you know exactly what port to look at in order to capture all of the unencrypted data. Passive mode, on the other hand, allows for a dynamic port to be used, so the data itself will be transferred over a different port. So it's an enhancement to the FTP protocol. So nowadays, most commonly you'll see port 21 used for the server commands, and then a dynamic port range in the thousands for the actual data itself. FTP is like that, where it separates the commands from the data on different port numbers. Not every protocol does that, as we've seen with HTTP, for example, runs commonly on port 80, and it sends commands and data on the same port. Not the case with FTP. FTP is a very old protocol. So we see a response from the server saying, all right, we're entering passive mode. I then ask for a list of the directory that I'm in. Remember, I asked for what directory I'm under. Print working directory. I switched to binary mode. I said, let's use passive. Now give me a list of all the files. The server then says, okay, I'm sending the directory listing. The directory listing was sent. So this is from the server. And then below here, I had asked to change directory to a subfolder called pub. And at that point, I stopped the capture. What we're missing, though, is the data. You notice I don't have any data here. How do I find the data with a dynamic port number using FTP passive mode? You do that by adding an additional filter to your display filter. You see that we have FTP. FTP is for the commands. If you want the data as well, you're going to have to do space, pipe, which is for OR. So FTP or FTP-data. If you push enter, now we're getting the FTP traffic as well as the FTP data traffic. So you can see that my client requested the listing of that directory, the root directory, and now the server is sending all of that data over the special port. So we can see that the server is running on port 54,536, and it's going to my client running at 52.285. So that's the difference between FTP active and FTP passive. Now there's also FTPS and SFTP. If you notice, all of this is unencrypted. We see all the commands, we see the login username and password. This is not good for going over the public internet in a non-anonymous mode. If you're using a username and password, you should be encrypting that. You should be encrypting your data. So you do that using SSL or TLS, just like I mentioned with HTTP, as we've seen before, and many other protocols that you can encrypt with TLS, the same thing. So FTPS, and it's very complicated because a lot of people get confused about this. FTPS is FTP encrypted with TLS or SSL. That's the more standard method of doing that, using the FTP protocol as it's already implemented, but then encrypting on top of it. There's also SFTP, which is the Secure Shell File Transfer Protocol. SFTP runs over a different port. It runs over port 22. So you'll actually want to filter based on SSH in that case, because the FTP traffic is traveling over SSH, the Secure Shell port. So you could use SSH as your filter. Now obviously that's not here in this capture, But that was the filter that you would use, and all of the traffic would go over that. But it would all be encrypted, just like with FTPS, it's encrypted. You would need the server private key in order to decrypt it, like you saw in the prior video with HTTPS. So note that there are those two protocols for transferring files in a secure manner, and they are different. FTPS uses the standard FTP, but encrypts it with TLS or SSL. SFTP is its own animal. It is its own protocol and application. SFTP is completely separate, and it runs file transfers over SSH. In this section, we discussed DHCP, how that protocol functions, and how to take a look at some of the options that are in it. We looked at HTTP, both in an unencrypted fashion and an encrypted fashion, and how to decrypt that. And we also talked about FTP and all of its many flavors, active mode, passive mode, and the encrypted flavors of FTPS and SFTP. Our next section, Application Protocol Analysis 2, we're going to continue with some additional application protocols that you will run into. Hi, and welcome to Section 2, Getting Started. In this section, we're going to take a look at what's new in Wireshark 2. There's a new version out, new major version that has many interesting features. We're going to take a look at how to capture some traffic, how to save and export those captured packets, how to annotate them, which is a newer feature, and print them, as well as some interesting videos on how to set up and use remote capture using libpcap running on a remote system from where the Wireshark GUI is running. This is video 2.1, What's New in Wireshark 2. Here you can see the new Qt GUI. It looks very similar to the legacy GTK GUI, with a few little tweaks. This main menu bar here has had some icons changed and removed. The general interface is a little bit cleaner. All the general functionality though is all the same. It's very, very similar. Capture options are up here in this gear. Click on this. You have multiple tabs for input options and output options and general options. Here you can see the preferences window that's been cleaned up. A little bit easier to navigate and view what you need to see. Here on the left side you can see the related packets diagram showing up based on what you select. So if you select different packets, this will change in size and shape and what might appear for you based on what you select. Makes it easy to pick out packets that are related to each other without having to follow TCP or UDP streams. Under the statistics menu, many of these statistics options now have a similar looking window. If you look at how the buttons and the filters and the general interface is set up, they're all now standardized and look very, very similar to each other, which I'm sure makes coding much easier for those who work on the Wireshark code. Here you see the Wireshark I/O graph, and in the bottom left here you can click on this plus icon and you can add multiple items to chart on your I/O graph. You can do so to an unlimited amount. Additionally, any changes you make in here are saved to your profile. With this graph you can also save as and select many different file formats to choose from. The follow stream dialog box, whether it's a UDP or TCP stream, has been updated so that it now allows you to select whether it's the entire conversation or just one side at a time, as well as allowing you to search for text within here. So we could search for peer, and you can see it goes through that. Here you can see the context-aware hints in action. Within this stream, if you look at the bottom here, you have some information that changes based on what you're hovering over. So you can see packet 503, packet 7, and if you click on them, the main capture window will change to that actual packet. Very handy for jumping through the data and being able to see it in relation to the entire capture. In this video we went over the major changes in Wireshark 2.0, and up next we are going to be capturing traffic and getting those first packets in that main window. One of the first things I'm sure you want to do in Wireshark is to begin capturing some traffic so you can get used to the utility and possibly diagnose some issues on your own network. In this video we're going to talk about exactly that. where to capture that traffic, and how to capture that traffic. Wireshark needs to receive the packets in one way or another so that you may begin analyzing the data and performing your network diagnostics. There are several ways of doing so in Wireshark. One way, which I will show you in just a minute, is to begin capturing on a local device with Wireshark installed through the GUI, the graphical interface. You also have the option of doing so through command line, which you'll learn about later on in the course. You can capture remotely from a Wireshark install on a management computer, for example. It can retrieve the packets being received and sent from a device somewhere else on your network using a special driver install. You can also capture the traffic in line on the wire, meaning you place a device called a tap somewhere along the data path that you need to diagnose, and it will then send that data back to your diagnostic utilities, one of which could possibly be Wireshark. And lastly, in the advanced section, I'll go over how to store packets locally on a internetwork device, specifically a Cisco router or switch, for export into Wireshark as a PCAP file. In order to capture traffic in line for Wireshark, you need to place some sort of device on the wire where it can see the traffic being sent and received, and then replicate that traffic out additional ports for your diagnostics machines, which might be possibly running Wireshark, for example. One of those early devices that we could use for older networks that were running half duplex is the hub. The hub is the predecessor to the switch, and it has a very basic functionality where it sees the electrical signals being sent across the wire, and it replicates those electrical signals out all the other ports that it has without any care as to what's on those actual ports. It's just a splitter, basically. That's great for a slower, older half duplex network, but for a modern switched full duplex network, you'll need something a little bit fancier. One of those that you could use is a tap. And you see here there are 4 different taps that I have listed. You have non-aggregating taps, aggregating taps, regenerating taps, and link aggregation taps, and each one has a different function. I mentioned span ports or port mirroring. In a modern switch network, this is a very common way of receiving traffic. If you have a managed switch, such as a Cisco switch or whoever's it might be, you can go into the switch and tell it to replicate the traffic that it sees on one port to a different port, and then that different port could be then connected to your Wireshark machine to capture traffic. It's very, very useful for modern networks because there's no other hardware required. You can just go into the switch and tell it to replicate the data out to your monitoring system. In order to capture traffic on wireless, you need to be aware that there's multiple modes that you could use. There's 2 modes that I'm going to talk about: monitor mode and promiscuous mode. Monitor mode receives all packets on a specified channel. So in the US we have 11 channels on 2.4 gigahertz, for example. You could tell your network card, the wireless card, to receive all traffic on channel number 3. Then it would capture all of that traffic for any SSID, any network that is on channel 3. Any traffic on channel 3, it would capture. You also have promiscuous mode, which is more common to be able to find in your wireless drivers, and it allows you to receive all packets on a connected SSID, on a connected network. If you're connected to your work network or your home network, whatever it is you're trying to diagnose, it'll capture anything that's traversing that network name, that SSID. But it will ignore any others on the same channel. And it will certainly ignore anything else on any other channel as well. So here we have Wireshark running. This is the latest version as of recording, 2.05. And you see I have a list of interfaces here, including a local area connection and some virtual adapters. I do not have any wireless adapters on this computer, or else they would show up here as well, and any other additional NIC cards that you might have, wired cards, doesn't matter, they'd all show up here in a list. You also see that there's a chart that's continuing to be drawn by Wireshark, and it's showing me the amount of data that it sees on each connection. This is actually pretty useful, especially if you have a diagnostic computer that has many different interfaces to different span ports or whatever it might be. Maybe you turned on span to a specific port that's receiving a lot of data, and you don't know which one it's connected to on the monitoring system. You could take a look here, and whatever port is receiving the most data, or the expected amount of data, that might be the one that you want to try and capture on. So I find that useful on crowded systems. In order to capture traffic, all you have to do in the latest version of Wireshark is double click that, and it will begin capturing your traffic. You can see that traffic begin to scroll by. In this computer, I'm not actually doing anything, which is very interesting, considering how much traffic is being sent and received, but there are services that are running in the background, and there's possibly minimized web browsers and such like that. But you'll see there's quite a bit of communications just on a standard idling computer. In order to stop this capture, you just go up to the top and click on the stop. You notice that the packets were scrolling by and being updated in real time. While this is useful for some situations, it might not be useful for all. So if you have a system that's receiving a lot of data, possibly gigabits per second, or if you're trying to run this on a computer that's very old and slow, that might not be an ideal situation, especially if you're using the GUI. So you can turn that off so it doesn't use the graphics card and the processor power to try and update this screen for you in real time. In order to do that, go up to this gear icon and go to the options, and you can see there's some checkboxes here we can turn off. So you can see the update list of packets in real time. If I uncheck that, that will prevent this list from populating as it continues to receive packets. And I can turn off automatically scroll during live capture. You notice the scroll bar on the right here went down to the very bottom, the latest packets that it sees. If I turn that off, it would remain up at the top. So those two things are very helpful to disable if you are running on an older computer like I mentioned. You can also select multiple interfaces. If you go back up to that options selection and you look at the input tab, you can select multiple interfaces with the shift key, or with the control key you can select them individually and then click start, and it will begin capturing on all of the interfaces that you selected. Depending on your situation, that may be a useful feature. In this video, we went over some different ways of capturing packets, how to get them into your Wireshark capturing system. Up next, we are going to save those packets and export them in various different ways. Hi, and welcome to video saving and exporting packets. In this video, we're going to take a look at how to save packet captures, how to save selected sections of packets, individual packets even, ranges of packets, how to export packets into other formats, and how to export raw packet data from the capture that you selected. Okay, here we have Wireshark up and running. Let's capture some traffic. I'm going to select my local area connection, and I could either double click as I mentioned, or I'll start the capture up at the top. And here we have some packets coming in. Again, I'm not doing anything right now on my computer. This is just what happens to be running in the background. And there we go, we already have a ton of packets out of the blue. So now if I want to save this capture, the entire capture, all the packets that I just captured, I'm going to go to File, Save As, and from here I can simply choose a file name. So we're going to call it Packets, and you'll see File Save As Type. Notice here it says PCAP-NG. So PCAP-NG is the next generation of the PCAP file extension. It was released with Wireshark 1.8, so relatively new, and it includes some additional features which we'll get into in future videos. But you should know that the PCAP-NG file extension is the new standard. So if you see a .pcap file with no ng at the end, that's an older capture file, and you can certainly save it as PCAP-NG going forward since that's now the default. And just be aware though that if you take a PCAP-NG file and save it as an original PCAP file, if you were to select your Save As type and you choose the original PCAP, you'll lose some of that functionality that comes with the NG format. So my recommendation is to stick with the NG format. Almost all plugins and additional software that utilizes PCAP files now support the NG format, so you might as well just use that going forward. You'll also notice along different capture extensions here, you have .gz listed, as well as with the PCAP-NG you have .gz, you have ntar.gz, and so on. In order to get that, you have to select the Compress with gzip option. So when you select compress with gzip, what that will do is, just like putting files into a zip file, it will take your capture file and try to compress it to make it smaller. So if it's a large capture, remember, a packet capture includes all the data that's traversed your network from your network card that you're capturing on. So if you were transferring a lot of data at the time that you're doing a capture, all that's going to be saved in your capture. It's going to be a 1-to-1 ratio of the data that's been transferred. So it could be very large. Gzipping that might make sense to you, because then it would be a much smaller file on your hard drive. Additionally, if you're trying to transfer the file across to your network, then they could potentially save time with trying to transfer the file, since it would be smaller to transfer. Most of the time, it's not used though. Especially if you filter out what you only need to see in a capture, and you end up saving only what you require, then they're usually very small. So I can save that capture. And so speaking of filtering out just what you want to see and making a capture smaller, let's do exactly that. So here we have some HTTP traffic, and we're going to right click on that, and we're going to follow our TCP stream. That way, just close that window. That way we have some sort of stream here that's filtering out all of the other data that's in our packet capture. So we've got 4 packets selected. If I want to save just those 4 packets into new file, I'm going to go to File, Export Specified Packets. And from here we'll call this packets small. And you'll see here we have a radio button to select between displayed and captured. So captured is the entire packet capture. That's almost 1,400 packets. Displayed is only going to save what's currently filtered and what's displayed in my packet list view. So if I have displayed selected and all packets, that's going to export all 4 of these packets into a new file. Additionally, I could select selected packet. So you'll see here I have packet number 13 currently selected, slightly different color here. If I choose selected packet, this will only save that one single packet into a new file. Or I could select a range. Now the range isn't going to show anything right now because we have our own little filter going. But what I can do is clear out this filter. And we'll go back to Export Specified Packets. And we could do packets range. And we could say packets 5 through 200. Okay, so there's 196 packets that are going to be saved into the packets range file. Additionally, you can export your packet dissections by going to File, Export Packet Dissections, and then choose a format you'd like. So we'll choose as plain text, and we'll call it packet dissect. We'll do just the selected packet. And so here we have our packet dissect text file, which you can see has the packet number, when the packet came in, it's just shown here as from the packet list, source and destination IP address, what the protocol was, any information about the protocols within it, and then the basic information that you can see here in the packet details section are now saved in the text below. If your packet capture happens to have captured any secured traffic, such as any HTTPS, SSL, SSH traffic, you can file, export SSL session keys, and you can then save those SSL keys for future use in some other application if you wish. You might have noticed one additional export that's grayed out. Export packet bytes. In order to get that to become selectable, you need to select the data, the application data, within your packet. So here we've selected our HTTP packet data, and if we go back to File, you'll see that Export Packet Bytes is now selectable. If I select that, I can now export my data from my packet in a raw binary format. Potentially useful if you're doing something with a hex editor or combining these pieces together for some other application. In this video, you learned how to save and export packets, either the entire packet capture subsets of that packet capture, such as filtered views, individual packets, as well as exporting raw data and to different formats such as text files. Up next is annotating and printing packets, where we're going to write little comments in our packet captures and use one of those new features of the pcap-ng file format and printing them in many different ways. Annotating and printing packets. In this video, we're going to take a look at how to use the new annotation feature, also known as comments, how to find packets that have annotations, and there's multiple ways of doing so, and how to print packets. Here we have Wireshark up and running. Let's get some packets to work with. I'm going to start a quick capture, and that's good enough. 30-something packets, or, well, actually 68. So there we go. To create comments for a packet capture, the entire capture itself, you can do so in the bottom left corner of Wireshark. You see there's two icons down there. One's a circle icon called the expert info we'll get into in a future video. And there's a pencil with a packet capture icon. And if you mouse over that, it'll say open the capture file properties dialog. Click on that, and that will open up a pop-up window that gives you a bunch of different information for the capture itself. And there's this bottom section here that says file comments. And here you can enter whatever sort of description you want for the entire packet capture. So maybe this is the capture from the management PC to the server. Data appears slow. Whatever you might want to enter here. Click on the Save Comments button, and those will save the comments for you. You'll also see that the file comment appears at the bottom of that top pane when I click Save as well. You can also create comments for individual packets. And to do so, you select the packet you want to create a comment for, right-click on it, and go to Packet Comment. You'll see there's a little pop-up window for you to enter your packet comments. So let's say this packet looks bad. Whatever you might want to enter here, click OK. When you do so, you'll see that in the packet details area, the packet comments section pops in and is nice and bright green, so you can see that. And if you expand that, it'll actually show you the comment that you've entered. Now if I select a different packet, that doesn't show up. So if I go back to the packet that I selected, it'll display again. Now you might be wondering, how do I find packets within a capture that have comments? Now there's multiple ways of doing so. One of them is to right-click on the packet comments field in the details area here. Right-click on that, and we're going to go to Apply as Column. And when you click on that, it'll create a column here, which will show you whether or not that packet has a comment on it. Now you'll see here on mine, this is showing nothing for packet number 7, and it does have a packet comment on it. There seems to be some sort of graphical bug in the version of Wireshark that I'm using, which is the latest version right now. So what I'm going to do is remove these columns, which created, and you can see it updated, but I'm going to remove the column, and we're going to reapply. And there we go, now it'll show it correctly. Packet comments column is there, and it says yes for packet number 7. So that looks good. Additionally, I can go to the expert info button that I was talking about in the bottom left, and when you click on that, it gives us a whole bunch of information about our capture, which we're going to ignore for now. That'll come in a later video, but at the very bottom there's the comment section, and it will say, hey look, packet number 7 has a comment, and it says the following. Now what's interesting is, if I move this to the side, and we go select a different packet, we're going to go all the way to the bottom and choose packet number 60. If I click on this comment, this packet number 7, you'll see that the packet list automatically jumps up to packet 7, selects it for me, and shows me the comment. Isn't that nice? A third way to find packet comments is to right-click on packet comments and then go to Apply as Filter, Selected. When you do so, it's going to filter your packet list by pkt_comment, and that's the field name for whether or not a packet has a comment in it. And you'll see here that packet number 7 is now the only packet showing, because that's the only one we've made a comment for. So if I were to clear this and we add another comment on another packet. Comment 2. If I reapply my filter on packet comment, now we see that we have 2 packets there. So that's another way of being able to find comments in them. You can simply filter by that with a display filter. In order to print your capture or print an individual packet, you can go to File, Print, and you'll see a number of options here which look similar to the Save and Export dialog. So what we can do is print a summary line for each packet, and if you uncheck this, you can see it actually changes the preview as you go, so you can kind of see how the file is going to look. There's a summary line which gives us information about each individual packet that's in the list, and the summary line looks kind of like the packet list view. So there's going to be one line which is packet 1, some information about it, another summary line for packet 2, some information about it, and so on. So that's actually a handy one to have on. Details, that's going to show you the packet details list here of the information about the different protocols. So we can turn that on or off. If I turn that off, that basically just shows us the packet list view. We're going to leave that on. And then I could also include the bytes if I really needed to. You're not going to want to do that for a lot of packets. Obviously your print would be very, very, very large. But you can see if I turn that on, it'll show you the actual byte information as shown in the bottom bytes display down here. So keep that off for now. And you notice in the bottom section here, just like we had with the export dialog, you can choose selected packets only, all packets. You can also mark packets, which was something I didn't go over before. But what you can do is right click on a packet and mark it, or do Control M. And you can mark a whole bunch of them. And they can be anywhere in the capture, it doesn't matter where. They don't have to be contiguous. And we'll mark up a bunch. Now if I go to the print option, you'll see that I have the option for marked packets only. So now it's only the packets I care about. So that might be useful if there's a specific issue that you see within a capture and you only want to print out those specific problematic packets, mark them, and then select marked packets only, and then you'll only print those, 6 for example, or 7 that I have listed here. So we can do that. We'll go ahead and print this. And you see here that file that we printed. I printed it as a PDF, so that would be easy to show you. You can see here the summary line for each packet is displayed. This is that summary line, which is basically the packet list line. And we've got the packet number. We have when the packet came in, the source and destination, the protocol, and so on, as well as those details that we also told it to print. So that's the real basic detail information about what protocols were involved in that packet that it captured. And it goes through packet 6, packet 7, packet 12, whatever it is that I selected, because I had printed those marked packets. So this is the selection of packets from the capture. So in this video, you learned how to create annotations and comments for your packet capture, as well as annotations or comments for individual packets, how to view them and find them in different locations in the interface, such as on a column or a filter or within the packet details view, expert information, and additionally, how to print packets. Next up is remote capture setup. We're going to go over how to capture your data from a remote machine from your Wireshark GUI, running libpcap on that remote machine. Remote capture setup. In this video, we're going to take a look at prerequisites for using remote capture, specifically with WinPcap, which is a Windows port of the libpcap library, and configuration of remote packet capture on the remote device. The first prerequisite is to install the pcap libraries. I'm using a Windows computer here for our test machine, so I'm going to install the WinPcap libraries, which are a Windows port of the libpcap libraries originally written for Linux. So what I'm going to do is go to winpcap.org and download the WinPcap libraries. Once it finishes downloading, go ahead and just click next to the installer, and there's no need to customize anything there. Note that the WinPcap libraries that are installed also come with Wireshark when you download Wireshark as a bundle, So if you already have Wireshark installed on the system, most likely you already have PCAP installed as well. The next step is to set up a local administrator account, which is going to be a service account for the PCAP service, the remote PCAP service that is running on this remote system here. That is used in the authentication on the system that's running the Wireshark GUI when we add the remote interface. In order to do so, we're going to press the Windows key and R, and it's going to bring up the run command. And in there I'm going to enter control space user passwords 2. Go ahead and click OK, and we will go to advanced. Click on advanced again, go to users, and we're going to make a new user. We will call this PCAP. We'll say it's a service account and give it a password. I'm going to uncheck the first option there to force the user to create a new password, since this is a service account, and we are also going to prevent it from changing its password and never expire. Certainly don't want the password changing on the service account as we're trying to use it. Now that we have our PCAP service account, we need to give it administrator privileges. So we do that by right-clicking on PCAP, go to Properties, click on Member Of, and we're going to click Add. Type in administrators, and go ahead and click on Check Names, which tells it to verify the group administrators is correctly typed in. Everything looks okay. Click OK. And we can go ahead and click OK again. Now the PCAP service account has administrator privileges. The last step for setting up the remote WinPCAP service is to press the Windows key again and R. We'll bring up our run prompt, and we're going to type in services.msc. Go ahead and press enter or click OK. And we're going to scroll down until we see Remote Packet Capture Protocol v.0 Experimental. Although it says v.0 and experimental, this has been a service that has been available for a long time now, and I've never had any problems with it. Go ahead and right click on it, go to Properties, and click on the Logon tab. We're going to select the This Account radio option, and we'll browse to the PCAP user, or whatever you named yours. You enter that and click Check Names. It verifies that that's the correct spelling, and it found the account. And then we're going to enter in the password that we gave it. Alright, click OK. It'll say it's been granted service rights. That's good. And at this point we can tell it to start the service. You can do so by clicking on the little play icon at the top, click on the Start shortcut there, or right click on the service and tell it Start. Alright, it should say running at this point. What I like to do, just in case, is to go up at the top here and click on Refresh, and just refresh a few times, make sure that service didn't crash at all. So it looks okay, and so it's running right now, and it shows the PCAP user as the logged in service account. At this point, everything is set up and ready to be used. The last thing to check is to ensure that the Windows firewall is either turned off or port 2002 is enabled to pass through the Windows firewall. For simplicity's sake for this, we are going to turn it off. So push the Windows key, bring up the Windows Start menu, and we're going to search for firewalls. So in Windows 10 here, you can just type and it'll start searching. We're going to go to the Windows Firewall in Control Panel, and you'll see here that is currently enabled. So we'll click on Turn Windows Firewall On or Off, and I'm going to turn it off. Click OK, and we can close that. And that's all there is to it to set up a remote PCAP system. So in this video we've gone over all of the configuration and installation needs for a remote system. Next up we're going to go over the remote capture usage and how to set that up in a Wireshark GUI and start capturing traffic from our remote device. Remote capture usage. In this video, we're going to take a look at how to use that remote packet capture software that we set up with WinPCAP on the remote system. In order to use that remote WinPCAP service running on the remote system and capture packets from it, we need to add that into our local Wireshark interface so that we can capture it. So in order to do so, we're going to go to our options, click on that, click on Manage Interfaces, and you see here there's the Remote Interface tab. Click on that, Click the plus icon in the bottom left here and enter in the host IP address of that remote system. I happen to know the IP address of that system I showed you earlier, and the default port used for this service is, as I mentioned, 2002. Click on the password authentication radio button and enter in those credentials for that service account that we created. So that was PCAP that I used. You can enter in the username and password there, click OK, and at this point it should show us the remote interfaces that it sees on the other device. So you see here that's my 77.155 device, and here's the interface that it detected. If you do not see this at this point, or you get a pop-up saying that you have some sort of connection error or it can't connect to the remote host or anything like that, make sure that service is running. Remember, when we set up the service on the remote system, it was on manual for the service. It was not automatic. So there's a good chance the service stopped or the system was rebooted or something like that. Go over there and make sure that service is enabled. So go ahead and click OK, and you'll see that shows in our interface list here. And we can go ahead and click Start. And that's all there is to it. So in the Getting Started section, you've learned a number of skills in Wireshark, including what's new in Wireshark 2, and as some features from 1.8 that I mentioned, how to capture traffic on a local Wireshark installation, how to get the packets to your Wireshark installation through different means such as span ports and such, saving and exporting those packets in different ways, annotating or adding comments to the packet captures and individual packets, and printing them or selections of them, as well as setting up the remote packet capture with WinPCAP on a remote Windows system and using that packet capture from the remote system to a local Wireshark installation. Our next section will go over the various ways of filtering traffic, both with the capture filters as well as display filters and additional ways of filtering things. Welcome to Section 9, Application Protocol Analysis 2. In this section, we're going to take a look at some email analysis, including POP and SMTP, some 802.11 or wireless Wi-Fi analysis, and some VoIP analysis for voice over IP telephony, as well as being able to play back the captured traffic in a VoIP capture to be able to hear the issues that may be occurring in it. Welcome to video 9.1. Email analysis. In this video, we're going to take a look at what POP and SMTP are used for, as well as investigating the communications in POP and SMTP and what some of the codes are, whether they're successful or error codes or something like that. Now we have three main protocols that we use for email on the internet. We have the Post Office Protocol, or POP. We have Simple Mail Transfer Protocol, or SMTP. And we have the Internet Message Access Protocol, or IMAP. These three are used by clients such as mobile devices or software running on a computer, some sort of standalone application like Thunderbird or Outlook or something like that. There's other protocols as well if you're dealing with Outlook for Exchange, for example, but primarily if you're using a generic application and you're accessing your email server in a generic fashion, you'll be using one of these three protocols. We're going to be focusing on POP and SMTP. POP is used for retrieving mail from a mail server, and SMTP is used for sending mail to a mail server and sending mail between mail servers. If you'd like to learn more about POP and SMTP, take a look at these RFCs. We have RFC 1939 for POP, and we have RFC 2821 for SMTP. In these you'll see there's a number of commands that are transmitted between the client and the server in order to convey what they want to accomplish in the connection. Just like we've seen with HTTP and FTP and some other protocols, there's an agreed upon language that is used in order to execute certain things. We're going to take a look at that in a packet capture. Now, it's very common in modern use to encrypt your data, especially email nowadays. So POP is often encrypted with SSL or TLS. You also do the same thing with SMTP or IMAP. All these protocols now you can encrypt with SSL or TLS. This is an unencrypted communication so that we can take a look at all the commands that are passed back and forth. What we see here is we have in the beginning a three-way handshake for TCP. POP is transmitted over TCP. And then we have our POP communications as well as some acknowledgments here, and then the fin closure down at the bottom. There is a filter for POP. Now, of course, you could right-click on your protocol here and apply it as a filter, or you can simply enter POP, and that will filter your traffic. But if you notice, I've now lost the handshake information. So the handshake at the beginning and the end, and some of the acknowledgement packets that were in here in between the data, those are now removed because they weren't part of POP. They were TCP acknowledgements and handshakes and stuff like that. So it might be better if you determine the addresses that are in use or the port that is in use, and you end up filtering on that instead of POP as the display filter. So what we have is our three-way handshake. We have our client and server. The client is requesting a connection. The server says, okay, no problem. The client then says, okay, I acknowledge the connection, and we have a three-way handshake. After that, the server then responds and says, okay, we are connected with POP3. The server is ready. You can see that in the info section. If we expand our post office protocol here, we'll have some more information. It says server is ready, so that's good. That's a good message. The client then passes its user. Now you see that since this is unencrypted, the user is in plain text. We pass the user command to the server. The server responds and says, okay, the username is good. Please send me a password. We then send a password. Again, this is unencrypted, so it's in clear text. And you can see it's very easy to determine what's going on. We have literally the commands are named user and pass and okay and things like that. Server responds and says, okay, mailbox has been opened up. Thank you for your credentials. You have one message that is unread. The client then asks the server for some status. The server responds with its status message. We then get a unique ID listing. And then the client asks for a list. This is a list of whatever's in the mailbox. Mailbox scan is completed and it sends us the following data. This is the number of messages and the number of bytes. The client then says, all right, let's retrieve message number 1. The server then says, okay, here's the octets that you requested, here's all the data. And you can see that down below. In the details here, we have not only the number of octets, but we have the actual email itself. Here's the header information, here's the sent and received information, there's the from, the to, the subject, the date, and then the actual data inside the email itself. And then as we see here, the data then continues. So here's the first packet was basically the header information with the beginning of the data, and then the data continues. And we have data, 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 data. And we acknowledge the packets, we keep retrieving data. Then the client says delete the message. I've downloaded the email, delete the message. This is an option that is changeable in your client. You can tell it to leave the message on the server, but traditionally it is done so that you download it locally and you would delete it off the server. Nowadays, with our web-based email, if you're using Gmail or Yahoo or something like that, we now most often leave everything on the server and have it archived there, but this is a very, very old protocol, and so it was based on local storage. Server responds that it deleted the message, and then we quit the connection and close out. It says, okay, sayonara. Then finally, we close out the TCP connection with a FIN-ACK series. Let's take a look at SMTP. SMTP is used, as I mentioned, to transfer mail between a client and a server in order to send it to a recipient. What we see here is a series of syntax of a user creating a TCP connection for SMTP. And then we see the SMTP response from the server. And of course we have SMTP listed in the protocol field here, and we could filter on that by simply typing SMTP. And then if we do that, again, just like with POP, we're going to lose some of the information there from TCP, so it might be better to do your filter based on IP and port. But what we see here after the three-way handshake from the server, the 128 address here, is it responds with a 220. A 220 response code is a service ready, meaning everything is good. This is going to look familiar to POP and to HTTP. Many of these protocols that are, especially the ones that are older, they use these different numbered response codes. And so just like with HTTP, 200 series response codes are good. So we see a 220, everything's good to go. And we see in here that we have eSMTP. This is for the enhanced version of SMTP. Just like with POP and FTP, SMTP is a very old protocol and it's been extended and enhanced over the years. And so there's a newer version of SMTP which is transmitted using new commands with an E in the front. The client then sends an ELO, EHLO. ELO is the enhanced version of hello, HELO, for the traditional original protocol for it to create a connection. The server responds to the hello request and it creates a connection. We then acknowledge that, and then the server responds with a listing of what it can do. There's some features that it has. We see that it has pipelining. Pipelining is an option in the server that says that it can accept multiple commands without having to wait for each one. So our client can then send a number of things at once and it doesn't have to wait. Our client then says that it's going to create a mail message. And if you notice here, it says mail from. That's actually, if you remember when we looked at the POP message, there was a from and a to and a subject and the actual body field. Exactly what you saw in the POP request, you see here in the SMTP. So we have the prepended command of mail, but you see from : and the email address, just like you would when you open it up in your client software after you pull the message. We are literally writing an email with commands right here. The email itself is not like a data package that is just bundled up into a little file and is sent to the server. This is old enough that we are actually crafting the email command by command and line by line in SMTP. So we are saying we're creating a mail and it's from the following person. The server says okay, looks good. Receipt to, so we are sending it to the following person. Server says okay. We then say here's some data, the data being the body of our message. The server responds and says okay, and let me know when you're done with the email message by putting in the following commands at the end of your message. And then the client provides a number of packets here of the actual email data that it wants to have in the body. See some additional packets related to that. We have some acknowledgments from the server for some of those data packets. Then a response from the server saying that the message was accepted and it's going to send it to the recipient. We acknowledge that and tell it okay, I'm done, and we quit the SMTP connection. Then we finish out the TCP connection with some finax, and we have some explicit resets here at the end as well. And that is the termination of our connection. Our next video we're going to look at 802.11, also known as wireless or Wi-Fi. Welcome to video 9.2, 802.11 analysis. In this video we're going to take a look at wireless connection issues and how they look in Wireshark. The 802.11 standard has been around for quite some time. It originally started back in 1997, you can see here, it was when it was ratified, and it was begun in 1991 actually. Since then it has had many changes to it, including 802.11a, which some people may remember. We have the 802.11b, 802.11g, and so on. As we go up in time here, you can see how many different flavors of 802.11 there are out there. Now, not all of them have been used for normal home networks or office networks. Some of these are specialty versions for long distance or low power or something like that, WiMAX, etc. You can see all these ones I've been going through have been superseded by a newer version. And those newer versions are up here. These are these ratified standards. So you can see that even though 802.11a and b and g and n are still supported by hardware out there, still supported by operating systems. The actual standard is, for example, for this version we're talking about, 802.11ac. So AC actually encompasses the AC standard, the N, the G, the B, the A, and so on. And you can see there's additional versions of 802.11 that are here, such as one that's going to be used for what's called the TV white space area. So these are sections of bandwidth that are available for potential use and reprioritization by the FCC. And we have some additional ones up above which are proposed standards such as AH and AI, and there's all these other ones out here to give us additional methods of connecting over longer distances and greater speeds and things like that. So all of this is available on the IEEE website, and you can learn much more about it at IEEE802.org. Additionally, PAC Publishing has a number of wireless related books and video courses that you can take a look at and continue your education in wireless networking. So this is an example of a packet capture done by a device that could capture the 802.11 frames and provide them to Wireshark. This is commonly done with a wireless card that is capable of not only enabling promiscuous mode but monitor mode in order to view all of the data that we want for all of the different channels that we use. Additionally, there's spectrum analyzers out there, such as Wi-Spy and others, that are dongles that you can attach to a laptop or something like that you can go around and investigate the spectrum analysis side of things. So we're looking at packet captures here, but remember there's more to it than just the packet captures. Wireless brings in a whole slew of additional issues, such as signal strength and interference with other devices and stuff like that. But looking at the actual data that shows as essentially Ethernet, it looks like Ethernet to us when we capture it, and that's done on purpose in the 802.11 standard, is that it's supposed to look like Ethernet but over a wireless connection instead of a wired connection. That's to make our life easier, make it more cross-compatible. What we see here in this capture is we have protocol right here listed, 802.11. So Wireshark knows that it's an 802.11 capture. This is an 802.11 frame. And it's a beacon frame. And if we expand the 802.11 section here, we see it's beacon frame, and there's some flags. We have a frame control field. We have the receiver and destination. It looks very similar to what you'd expect on layer 2 on a wired network. You have a from and a to MAC address. You've got some additional information, some additional flags and stuff like that. Now, of course, there's some other options in here for it to work on wireless, such as our BSS ID, what device we are connected to, what access point we are connected to, what kind of frame this is, because there's different kinds of frames in 802.11. We of course have our frame check sequence, just like we had with the standard Ethernet. Now, what is a beacon frame? A beacon frame is transmitted normally every 100 milliseconds by an access point in order for it to declare to all of the listening devices that it is providing the following network, that it is beaconing that it can support the following network name. And so you see lots and lots of beacon frames in a wireless capture. They occur constantly. If you do not see them constantly, then that is a potential issue. Now, if you want to filter, if you have a packet capture that includes other erroneous packets in it and other frames, if you want to filter only your wireless traffic, you can do the WLAN filter. If you use WLAN, that will include all of the 802.11 protocol frames. Something else that you might also want to do, what we'll do is we'll leave WLAN on, and what you might also want to do is not show beacon frames. Let's say that you know for a fact, after looking through things, that beacon frames are consistent and everything is good with them. I don't have to worry about them. What we'll do is select the beacon frame down here in the type, and we're going to apply that as not selected. And that way, we are selecting all of the wireless LAN frames, but not anything that is a beacon. And that really trims down our capture here, so we see only the probe requests and responses and some data. Speaking of beacons, here's an example of a capture with a whole lot of beacons. Everything is just constantly beacons, beacons, beacons everywhere. A common problem that can occur in wireless is a drop in beacons due to some sort of problem on an access point. Maybe it's a signal strength issue, maybe it's a problem with the firmware on the device, a bad antenna, who knows, it could be anything. But a drop in beacons will cause clients to drop their connection to the wireless network because they think the wireless network has disappeared. So here's a capture that includes a problem with beacons, but we don't really see anything pop up that's obvious. Nothing's bright red popping up to us. There's no changes really. It's just all consistent. So how do we see the problem? Remember back to the video on statistics. We can go and do an I/O graph on our beacons, and we can see that we absolutely have a drop here that shows us we've got a problem with our access point. So make sure you certainly use your graphing capabilities when doing wireless troubleshooting, because there's a lot of variables that are not controllable by us due to the nature of it transmitting over radio waves. So we have to do a lot more visualization in order to see what's going on, especially when you have thousands and thousands of frames like this and there's a problem in there but you don't know where and exactly to what extent. Using graphing and such can be a very big help for you. Additionally, we have a capture here that shows a signal issue. So here we're doing a ping. So we have a ping request and a reply, and we just go ping, 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 and we keep pinging. Now what I want you to do is take a look at this as I scroll down and let me know if you see anything that's odd or an obvious problem. We're just scrolling through. This is all echo pings. Request and reply, request and reply. Do you see any problem here? I see a very obvious problem. As I scroll through, look at the fact that we have so many requests and very few replies. That is a very blatant problem. And if we go into the expert info, we can see in the warnings that it says no response seen to the requests. And of course, as we click through each one, it's going to show us each packet along the way. We have all these requests that did not receive a reply. But you don't see any other problems in here in the capture. Now remember, ICMP does not offer any sort of stateful connection like TCP does, for example. So we don't get any responses that there's really any problems. Just we do the attempt, it fails, and we just keep attempting over and over again. So being able to take a look at what's in the capture, even just scrolling through it and taking a look at what the pattern looks like, can be useful. Because we don't really have much else to go on. Now of course you could also graph this out and you could have two graphs, one of them requests and one of them replies, and you can see how they may not match up in the I/O graph. This is indicative of a signal issue. So what we're looking at here is we have some data packets that are making it and some that aren't. But in the capture, it's not going to tell us the signal strength anywhere. So we have to determine what the problem is based on the information we have. And from looking at this, it looks like a signal problem because we have packet loss. Now on the testing device, you'll most likely see that in your command window. It'll say that so many packets have been lost during the following ping attempts. And in the drivers, you may see that the wireless signal is low. So there's other ways you can look at this, but if you're looking at just a pure packet capture of ICMP, here's an example of what a problem would look like, such as a low signal issue. Wireless is a vast topic that is very in-depth, and I highly recommend you spend time going through a full wireless course or series of books to learn it if you are going to end up supporting that and that's something you're interested in doing. A short video on how to look at it in Wireshark and what certain things might look like in a Wireshark capture is useful, but there's much more going on with wireless because of the nature that we're using radio waves and signal strengths and such are such a problem. So I highly recommend you go out and learn more about wireless in order to understand how things really work behind the scenes. Our next video is going to be on voice over IP, and we're going to take a look at how a SIP connection works, and it sets up the call for a voice over IP phone call, and how the RTP protocol then creates a connection between the devices to send data. Welcome to video 9.3, VoIP analysis. In this video, we're going to take a look at how SIP works when a connection is created between two phones, and how RTP works to transmit the live data between the two. The example capture that we're going to use for this video and the next one is available on the Wireshark sample captures page. If you scroll down and look for the SIP and RTP section, we're going to use the Magic Jack short test call. Download that and open that in Wireshark. Once you have that open, we'll take a look at our capture here, and we see we have a variety of packets here. It has not been already cleaned up. And we see there's some ARP here, some UDP traffic, ICMP, there's some SIP and some RTP. We have some SMB at the end there. So there's a mixture of stuff. This is like a real capture. In order to pick out just the SIP traffic, which is one of many protocols, but the most common protocol to use for VoIP, we simply enter SIP for our display filter and apply it. There's a number of other protocols in use as well, such as Skinny, which is a very popular one for Cisco networks, but the standard one is SIP. So what SIP does is it creates the connection between two devices. And if you see on the left here, look at the time column. We have 159 seconds. So what we have here is one series of connection attempts, because it's all very quick, very much in the same time frame. Then we have another packet, 166 seconds, and then we have another couple in the 170s. It's important to note because we're missing some data here. If you remember, as I was scrolling down, I said there's also some RTP traffic. What happens is SIP creates the connection between the two devices, but then the actual data, the video traffic or the voice traffic, whatever it is transmitted over the real-time protocol, RTP, directly between the two devices. So if we're filtering on SIP, we're not going to see it. So what we need to do is add RTP to this, and that'll flesh out some of this missing time frame we have here. So there we go. We'll select SIP or RTP, and you see now we have our connection creation with SIP. We have RTP, which is the transfer of the voice traffic, and then we have some SIP goodbye commands at the bottom. And just like with the other protocols we've talked about, they use status codes in SIP just like with many of the others. So we have the 400 series, which is a problem. We have 100 series, which is a success. And there's some other commands as well. Of course, if you would like to learn more about SIP, take a look at RFC 3261, which gives you a great breakdown as to how SIP functions. What we see in our capture here, though, are a number of connections and then some actual data traffic sent. And this is actually a very good capture because it shows us a problem as well as a success. So remember I was talking about status codes. We have here a status 100 trying. And so what we have is a local device, which looks like some sort of phone, trying to create a SIP connection out to Magic Jack. It's providing an invite command saying, please invite the following device into the connection. And this is being sent to this 216 address. It's being sent to the Magic Jack SIP server. The SIP server is handling the connection between the one phone and the other phone. And then once that connection is established, it then is hands off with the communication. It does not act as a proxy and pass through all the data traffic. It only creates the connection. So we can see that here we have 216.234.64.8. Our device is sending a request to it saying invite the following phone number, try to call it. The server responds back and says, alright, I'm going to try it. Oh, but you're not authorized. Interesting. We then have a second request here where the phone calls out to the server again and it says please invite the following number, I'm trying to call it. Server responds back saying okay, I'm trying it. I'm going to ring that phone. We then have a success and it provides us a session progress If we expand SIP here, we can see that we have session progress, so we have a success here. And we have additional data about who the call is from and to, as well as what's in the body. You can see in the body section here that we have media description, name and address, audio, what port using RTP. So here's where we are defining in SIP that we are going to use RTP to transfer audio traffic between these two devices defined in the message header from and to. Once that connection establishes, we see that our local phone here, this 192 address, is now connected to a different public address. Look at that last octet. We also see that we're using G711, which is the encoding scheme. There's a number of different encoding schemes out there. Some of them are better quality but with a higher bandwidth. Some are less bandwidth with a lesser quality. It's up to you as to which one you want to use, but G711 is a very common one. And we can see that down here in the RTP information. We have a payload type of ITU G711. ITU is yet another standards body. Just like the IEEE and the IETF, they define certain protocols and encoding schemes such as G711. So then we have a whole bunch of data packets between these two devices direct, all with RTP. And then down at the bottom here we have a connection request to terminate the connection. So there's a goodbye. And then we have a status OK saying that we terminate the connection. What we can do is take a look at these in the telephony statistics area. Anything you want to know about your VoIP traffic can be found under this section in Wireshark. One of the greatest spots to go look are either VoIP calls or SIP flows. Really depends which one you want to go into, but if we go into VoIP calls, we see here's the one phone call. If we had a bunch of phone calls happening at the same time in one packet capture, they would all show up here in a nice chart, and they would have what times they started and stopped, who initiated the connection, who's it from and to, what protocol are they using, and so on. What we can do is select that and go to flow sequence, and we can see a great diagram of what ports on the local side, on the local phone, what ports are on the remote side, on the SIP server, and what ports were used here on the actual device. You see there's 3 devices in use here. All the SIP traffic, remember, look at the right side here in the comments, you see what protocol is in use. All the SIP traffic goes to the middleman. Then once the connection is established, then we have RTP traffic, the audio traffic in real time, goes to and from those 2 devices on RTP direct. Then when we want to terminate the connection, we send a goodbye and then an OK to acknowledge that, and we've terminated the SIP connection. But again, remember, it occurred to the control server, the SIP server. I feel like this is a really great way of being able to diagnose what's going on in a phone call. And if you have a problem with your SIP connectivity with some sort of VoIP provider, taking a look at this and telling them what commands are sent and which ones are received is very helpful for the provider troubleshooting person to diagnose what's going on. They can compare what we see to what they saw, and it's very, very helpful, especially these commands. The 100 trying, the 200 OK, the acknowledgements, the goodbye, any of these commands here are very helpful. In comparison, we can take a look at the statistics flow graph. We looked at this before, and you see that the flow graph is a bit more complicated to look at. You can still get some of the same information from it, but it's more difficult to view since it's per packet. So I think it's better in my opinion to use the other flow graph. Even though we can adjust this to displayed packets, it's still for every single packet. So if you're just talking about the basic connectivity of the basic flow, the other flow graph is better. If you need extreme detail, you can take a look at that in here. You can also take a look at, under telephony, the SIP statistics. And the SIP statistics will tell you a count of how many different occurrences have happened of different requests. Remember I said there's different codes that are in use, just like HTTP and FTP and all the other ones we've looked at. Same thing here, and it will give us a count of how many times certain things have occurred. So this was the SIP responses, and then we have SIP requests, and you see that there are 2 acknowledgements, a goodbye, there was an unauthorized. And if you have a long packet capture with a bunch of problems, you can take a look at this And of course, you can sort that based on your count and see which ones are the most common. If you see a bunch of 400 or 500 errors or something like that, that might be a problem that you need to investigate. And just like with SIP flows, we can take a look at RTP, which is the audio traffic, the actual voice traffic, and look at the RTP streams in addition to the SIP streams. So remember, we had that one connection from the phone to the Magic Jack phone. We see that here in the bidirectional setup here. So we have the connection from my phone out to the Magic Jack, and then from Magic Jack back to my phone. And these are both RTP. The payload is G711, like we talked about before. It also gives us some good information about the jitter. The jitter is a very useful statistic to look at. The lower the jitter, the better things are for voice traffic. Any sort of packet loss that you have, which is also a column here, any sort of jitter that you have, any latency, those are all major problems for voice traffic, any sort of real-time traffic, video traffic, voice traffic, etc. Jitter is the difference in latency between different packets, and you have massive swings from one packet to another. You can have a lot of audio quality problems as packets are arriving at different times and get jumbled up in the software. You might have some packet loss as well in that sort of a situation, so then you're losing certain words and such, and that's when you start getting that really weird crackling problems. You get dropped words. You might have one side that's completely silent and the other side can hear. You can have all sorts of strange problems when you have a lot of jitter or packet loss. In this video, we looked at some VoIP traffic using SIP and RTP, how to filter on those, as well as how to look at some statistics and some flow graphs on them. Our next video is VoIP playback, where we're going to play back this Magic Jack phone call and be able to manipulate it a little bit to listen for problems in the actual audio transmit. Welcome to video 9.4, VoIP playback. In this video, we're going to reconstruct and play back VoIP calls and be able to listen to quality issues. What we'll do is use that same Magic Jack call that was used in the prior video. If you don't have that file, go to the sample captures on the wireshark.org wiki and download the Magic Jack short test call. One of the really great features of Wireshark, in addition to all of its many filters and statistics and graphs that it can create, is that it has the ability to play back voice traffic. Some people might find this kind of creepy if you're an end user, that you can listen to someone's phone call, but it is data. Just like we can read all of these commands back and forth, we can read the username and password if it's unencrypted. If the SIP traffic is also unencrypted, then we can listen to the phone call just because it's standard data. It just happens to be voice traffic. So we can do that in Wireshark here very easily. In order to do that, we opened up our call here. We simply go to telephony, and we're going to go to VoIP calls. Select the call. So there could be many of them here. So we can select the call and click on Play Streams. And when you click on that, you see a nice histogram of exactly what's going on in the voice call. This alone might be able to tell you something about what's going on once you get used to what certain things look like. If it's a phone that's ringing or actual words and discussions, you might be able to pick that out just by looking at the histogram here. And then of course you can select one side or the other to bring it to your attention so you can see what might be occurring on one of these channels or the other, whether it's the source to destination or the destination to the source from one phone to another. And so what we can do is leave everything as defaults here and go ahead and click play.
Testing. One, two, three.
And you'll see that that played back the audio of the phone call. Now it did play back both directions of that phone call, so we got to hear both the sender's side and the receiver's side. So what we had here in the top was the one side of the conversation, and then on the other side here is the other side of the conversation. So that's very useful to be able to actually hear both telephones at the same time. That way, if one user is complaining about something and the other one isn't, you can actually listen to that And you can listen to as if you had both telephones up to both of your ears at the same time. What you can also do is adjust the jitter right here in the player and listen to what that might sound like and what kind of problems might occur. Now, as you notice that this graph was real time, and as the audio played, you saw that playback line go across. Any other problems that might be known about in the capture, and this is a relatively clean capture, if there's any problems in the capture, they will show up on this graph, and you'll see them begin to occur as you change things such as the jitter buffer. So what we'll do is we'll drop that down to something very low, let's say 5. And you can see already that we have some silence that was created, as well as some additional errors. If we zoom in, we have some jitter drops that have also been created. And we've actually manufactured some problems in our connection. And if you zoom out far enough, you'll see there's that initial ringtone that occurred that was off screen before. And what we'll do now that we've inserted all of these problems in our packet capture, let's go ahead and play it.
Testing 1, 2, 3.
Now hopefully you were able to hear that difference. In the beginning of the phone call, we had a bit of a crackly sound. As the phone was ringing, we also had some kind of dropped packets there. You could hear it kind of was crackly and didn't sound that great. And the voice in the beginning there also had some words that were kind of clipped and missing. Additionally, the one side is completely silent. If you remember right, looking at the histogram, there was a duplicate of each word in the test 1, 2, 3. The one side now is completely silent. It's dropping all of that, and it's now completely missed because there's too much. There's too many problems in the jitter. So this is a great tool to use to be able to recreate different problems and be able to listen to what they actually sound like in real life. So in this section, you learned about some email analysis using POP and SMTP. We also looked at 802.11, which is wireless, and how certain things look like in a packet capture, and the fact that you'll need to do additional troubleshooting outside of what you can do in Wireshark in order to properly diagnose wireless. We also looked at VoIP analysis using SIP and RTP, creating that connection and then transmitting that audio data directly from one device to another. And then we also played that back using the built-in tools in Wireshark and manipulated some of the settings in that for jitter in order to recreate problems and be able to listen to what that sounds like. Our next section is advanced features, where we're going to use some command line tools and extend Wireshark and talk about some of the enhancements that you can do to it. Welcome to section 10, command line tools. In this section, we're going to take a look at running Wireshark from the command line, executing some of the arguments that you can use for it, running tshark, a command line packet capturing utility, running tcpdump, which is a common Linux application for also doing packet captures, as well as running dumpcap, which is another command line packet capture tool. Welcome to video 10.1, running Wireshark from the command line. In this video, we're going to take a look at how to run Wireshark from the command line and explore some of the command line options and how you might use them. First thing we'll want to do is open up a command prompt, and then we're going to browse to where Wireshark is. Unless you have Wireshark in your system variable, you won't be able to simply type Wireshark and have that function. So what we'll have to do is go browse to where it's located. In my system, it's back in program files and in Wireshark. And if we do a directory there, we'll see here is wireshark.exe, as well as some of the other tools that we'll talk about later, such as tshark. So what we'll do is run wireshark.exe. And if you push that, press enter, it will open up Wireshark just like as if you were to click on the icon. If you type Wireshark with a space and then -h, that will provide the output of all of the variables and arguments that it has available to it. And if we scroll up here, we'll see, alright, here's the version of Wireshark we're running, and here's a dump of all of the variables and arguments that we can use. And you'll see that they're broken up into different categories. So we have capture interface arguments, we have capture stop conditions, whether or not we want to output in some sort of fashion, if we want to process packets, if we want to open up Wireshark with a specific view in the user interface, if we want to output the file in a specific file name, or do any other miscellaneous things. One of the first things you'll want to do, most likely, is set up Wireshark to run a capture with your default interface, your standard local area connection wired interface. And you see that you would do that with Wireshark-I and then an interface. And it says the interface name or IDX. Now, how do you determine what the interface name is or what the IDX is, the index of what that interface is? And you do that with -D, print list of interfaces and exit. So what we'll do is run Wireshark-D. Note that the capitalization does matter. We'll do -D, and we see here we have index numbers. That's the IDX 1, 2, 3, 4, 5. And then we have the name after the unique ID of that interface. We have the name, local area connection, local area 4. We have the VMware network adapters, all the other stuff that's on my system. So we can then execute Wireshark with -I and then either the name or the IDX number. I like to use the index number just because it's nice and short and prevents any additional typos. So we'll do Wireshark-I 1. Simply press enter, and you'll see it doesn't really do much. So now the problem is, it's because we've opened up Wireshark, and by default, Wireshark opens up to this main home screen. And the main home screen doesn't actually have you do anything yet at that point. It doesn't, you're not starting a capture, you're not doing anything. You just open it up. Now, you see it does have the first interface here kind of selected, but it's not that useful. So let's close this, and we're going to tell Wireshark to start capturing the second it opens up using the interface that we've defined. And we do that with, if we go back to our help, we'll see we can do that with -K. Start capturing immediately. The default, which we just noticed, is do nothing. So it just opens up the Wireshark interface. So we're going to use -K. Here's -I1, so that's my first interface, the local area connection, and I want to use -K, and it will now immediately start capturing on that interface. Another useful feature is to run Wireshark and have it automatically create files after a certain file size or a certain duration of time, or after a certain number of bytes or anything like that. Most commonly, people run them in a ring buffer where you create a file and then it automatically switches to a new file every hour or every 30 minutes or every 10 meg, whatever it might be that you have decided is the best way to approach this issue and to approach this system that you're capturing based on the volume of data that you're expecting. So what we can do is execute Wireshark using this flag to allow us to automatically create files. This is very useful if you want this to run overnight and not crash your system by having a 20 gigabyte capture file in the morning. That's not going to be very useful and be very difficult to work with, if possible at all, depending on your system. And so what we'll do is run Wireshark with the primary interface that we've already selected, -I, number 1, -K, so it initiates the packet capture right away. And then we're going to define the fact that we're using a ring buffer. So we'll use -B for ring buffer and the kind of ring buffer that we want. Do we want file size? Do we want duration? What might it be? If we look up here, you'll see that ring buffer has a number of options such as duration, file size, and after the number of files that you want to replace them. Hence the term ring, where they replace themselves in the circle. But what we'll do is select -B for ring buffer, and we'll use file size 10,000. And if you do file size 10,000, the file size is based off kilobytes. So we're saying approximately 10 megabytes, make a new file. So every 10 megabytes, we're going to make a new capture file. We then have to define the output file. So we're asking for a ring buffer, but we need to tell it where to put it. So we're going to say -w for write to. We're going to write to an output file, and it's going to be located in users Andrew /capture.pcapng. And then if we run that, that will have Wireshark run and begin capturing all the packets. Once it hits 10 meg, it will then refresh the screen and start capturing again, and you'll see it just kind of flicker once every time it hits 10 meg and keep coming up with a new screen as it captures a new cap file. And if you go into the directory that was specified in the -w argument, you'll see all the files that were created every time it hit 10 meg. This is just an example of a few arguments and flags that you can use running Wireshark from the command line. As you saw, there are many options there, and you can create very elaborate custom ones if you wish. Up next, we're going to look at T-Shark, which is a command line only application that comes with Wireshark when it's installed. Welcome to video 10.2, running T-Shark. In this video, we're going to take a look at how to run the terminal version of Wireshark so that it only has a command line interface instead of opening up the GUI. In order to run T-Shark, you have to open up the command window, and once it's up, we have to browse to where Wireshark is installed, because as I've explained, unless you have it in your system path, it's not going to be available. So we're going to browse again to where it lives. And we do a directory listing, and we'll see here we have tshark.exe. This is installed by default with Wireshark. In order to run T-Shark, all you have to do is, of course, run tshark.exe. And if you do so, it automatically begins capturing on your default interface. You'll notice also that it shows the packets that it's capturing directly to the command line interface, directly to standard out. And it does so because it does not have a graphical interface. There's nothing for it to display to except for the screen that it's currently using, which is the command interface. And you'll see here that the output provides a similar display as you would see in Wireshark in the GUI. We have the packet number, we have the time since the pack capture started, we have the time difference between the last two packets, we have the source IP and the source port, we have destination IP, destination port, and so on. And if you take a look at tshark.exe-h, just like with wireshark.exe, it's going to look very similar. If we scroll up here, we have these same arguments that we can use basically. So we have -d to display the list of interfaces again, -i for the interface that we want to use. We don't have to define -k so that it automatically starts capturing because T-Shark doesn't have a GUI for us to do anything in, so it automatically starts capturing anyway. We can set the ring buffer just like before. We can define output files. We can do all sorts of things. And so for an example, we can do tshark-d just to display all of our interfaces again. So we confirm that we want to use interface number 1. And we'll do -i1 so that we ensure that it uses the first interface. And then we can define an output file as well. So we'll write this out to c:\users andrew test.pcapng. And now it begins capturing. And you'll see here that it's showing us how many packets that it's captured as it runs. In order to stop the capture, simply press Ctrl-C, and that will stop whatever it's doing. And just like with the Wireshark example, we can enhance this line that we've already created, and we can define a ring buffer, for example, and say duration is every 100 seconds. Then it will do exactly that. Every 100 seconds, it'll create a new file. T-Shark is very useful for things that you want to script. If you want to write a batch script or a bash script that will do a capture, and you want to ensure that it uses all the functionality that Wireshark is capable of doing, and it saves to the pcapng format, and you want to make sure that it does everything just like you would in Wireshark itself. Using T-Shark is a great use, as well as on systems that have low resources. So if you're running this on need to do a packet capture on some old system, like a Windows 2000 system or something like that, that's barely scraping by, you can run Tshark and it will eliminate a lot of the overhead that you have with running Wireshark, especially if the interface is automatically updating and scrolling with the packets. So this gets rid of all of that and it just gets the data that we need. Our next video, we're going to take a look at TCP dump, which is available on almost every Unix or Linux system out there. Welcome to video 10.3, running TCP dump. In this video, we're going to take a look at how to run TCP dump on a Linux system to capture traffic. If you have a Linux or Unix-based system, BSD, whatever it might be, that does not have Wireshark installed, and you do not have the option of installing Wireshark, or if you have a system such as this where you don't want to spend the time to install Wireshark and you just want to do a quick capture, you can do so on almost all of them with TCP dump. This is a very common utility that's installed on almost every single Linux-based system out there. So what we have here is a newer version of Ubuntu, and I've opened up the terminal window, and all you have to do is run TCP dump. It's within the system variable path, so you don't have to go browse for it like we had to for the others on Windows. And I'm going to run it with help, --help. And we can see the TCP dump has displayed its help contents and is showing us what arguments it has available for it to receive. And what we can do if you want to learn more about TCP dump within the own terminal window, if you're not familiar with Linux, you can do man TCP dump, and it will provide you the manual on how to use TCP dump. And so this is a nice long document describing all the different arguments and what they do and how to use it with some examples and such. To get out of there, you just push Q. Now you'll notice in the usage line that the syntax for TCP dump and the arguments and the flags that it has available are different from Tshark and Wireshark. So we can't run the exact same commands. They're similar, but they're not exactly the same. For example, there's no -D for us to take a look at our interfaces. If you want to know the interfaces on your Linux system, usually you can run something like ifconfig or iwconfig, depending on what you're looking for, and it will output the interfaces that you have available and the IP addresses associated to them and a bunch of other statistics. Now this is a virtual machine that's running right now, so that's why it shows ENS33 as the interface name. Quite often this is ETH0 or something like that. LO is our loopback on the system. Just like every other system you've seen in Windows and such, there's usually a loopback. This is loopback on this system. And so if we look back to our information here, we can run TCP dump, and then we can also define an interface with the -I. So that's where that interface comes in. So we would do TCP dump -I ENS33. Now by default, TCP dump without the -I command will try to run on the default interface that you have, the ENS33 interface in this example. And we can take a look at that here. When I try to do that, you'll see that I have an error. It says you don't have permission. Depending on your system, you'll probably have to run sudo in order to do this. And then enter in the password for your user, and then that elevates the privileges for your user so that you can run this command. So you see that it says the TCP dump is now running. It would show us right now any packets that are coming into and out of the system if they were, but because this is a virtualized system, TCP dump's not functioning correctly on it right now. So what we'll do is push Ctrl+C to cancel it, and you see there's 0 packets. What we're going to do instead is define the loopback interface for the example. So we'll use TCP dump -I LO for loopback, as we saw up here under the ifconfig command. So if I do that, now it's listening, but we don't have any traffic yet going to the loopback. So what we'll do is we'll open up a new terminal, and I'm going to generate some traffic. And what I'm going to do is simply ping my localhost. So localhost is a alias name to 127.0.0.1, which is my loopback address. So as I ping loopback, you now see that popping up in the TCP dump window. And you see that we have, similar to T-Shark and Wireshark, we have the time that the packet occurred, we have from and to, what kind of protocol is it, what's in the packet, what are the details in there. And we'll cancel that. Control C closes both of those. Now, if I were to do a listing, this is like dir in Windows, ls. If I do a listing, I don't have any files here besides the test one that I did earlier. So by running that, it outputs to the standard out to the terminal, but it doesn't actually save the file. In order to do so, we would have to define the file just like in T-Shark. So what we'll do is we'll remove my previous test file. And you can see that that's now gone. And what we'll do is we'll run tcp dump again. And this time we're going to define an output file for it to save to. So just like with T-Shark, luckily, we use -w for write, so we're writing to a file, and test.pcap. Now when I do that and I start generating some traffic, so now that instead of outputting to the standard out, it's outputting to the file. And I can stop my traffic, I can stop my capture, and it says it saved 64 packets. And if I take a look at my listing, I do have a test.pcap here. And if I look at the size, I'll see that it does indeed have some bytes in there. There's also an option with a capital W. And I wanted to point this out because I've been showing examples of ring buffers. This is a way of doing a ring buffer where it will automatically overwrite so many files. So it'll save however many you define, and then when you get to the maximum number, it will then start overwriting the last oldest file. Our next video, we're going to take a look at dumpcap, which is another option as another alternative to T-Shark or TCP dump. Welcome to video 10.4, running dumpcap. In this video, we're going to take a look at how to run dumpcap, which is another alternative to T-Shark and TCP dump. Once again, we'll have to browse to dumpcap. In this example, it is installed with Wireshark on this system. And if we do a directory listing, you'll see dumpcap is indeed listed in here. And T-Shark is actually based off of dumpcap, and so we can do dumpcap.exe and we'll --help or -h. If we take a look at the output, it looks very similar to T-Shark and Wireshark. Depending on the system that you're using though, it may only have dumpcap available for one reason or another, or T-Shark is using too much memory. If it's a really small embedded IoT system or something like that, you could potentially use dumpcap to have an even lighter utility in order to capture traffic. Or maybe you just like using this better. If we look at the arguments that are available, they are just like in T-Shark. We have -i, we have -d, we have -w for output. They're all very much the same. And so we can illustrate that by running dumpcap, and we'll do -d to display our interfaces again. We can do dumpcap, and we'll do -i1, and we'll output to a file again. So we'll do C users Andrew, and we'll use dump.pcap. And if we start doing that, it'll begin capturing packets. We can also expand upon this and define a buffer to use as well, just like the other examples. And we can do -b and say duration 60 seconds. This way, every minute, it will create a new file. We can also illustrate this by reducing the number of seconds. So let's change that to a 5. So every 5 seconds, it's going to create a new file for us. See how that file name is changing every 5 seconds? That's an example of using that buffer. Note that in all of these utilities, you can define filters that you can restrict the capture, so you can apply capture filters to these. I would not recommend doing that unless you really have to. It's much better, if possible, to capture everything and then filter only what you need with the display filters in Wireshark. by applying capture filters, you can potentially miss some of the packets that might be useful. Maybe you're only capturing TCP traffic, but then a whole big blast of ARP or ICMP traffic ends up causing a problem. You would miss that because you're not capturing that traffic. So I would highly recommend, if possible, to just capture what you can with the defaults here, using just a basic interface selection and maybe a ring buffer, and then taking those files and parsing them out and observing them in Wireshark. Just applying display filters and doing whatever you need, graphing it, and so on. In this section, we went over several command line options for Wireshark. We've discussed running Wireshark from the command line and some of the arguments that are available with it, running tshark, which is the command line version of Wireshark, running TCP dump, which is a generic dumping utility that's available on many Linux and Unix systems, as well as running dumpcap, which is another alternative to tshark and Wireshark. Our next section, troubleshooting scenario, is going to dive into an issue with a user trying to connect to an FTP server. Welcome to section troubleshooting scenario. In this section, we're going to take a look at troubleshooting a specific issue within Wireshark, and we're going to do so over a series of videos. First up, though, we're going to take a look at expanding Wireshark with some additional plugins and dissectors. We'll then follow that up with determining where to begin our packet capture about the troubleshooting issue that we're going to look at. We'll then capture the actual traffic, and then we will diagnose that traffic. Welcome to video Wireshark plugins. In this video, we're going to take a look at Wireshark plugins that are available and how to develop them. Now, plugins in Wireshark are dissectors, and dissectors are different ways for Wireshark to analyze and take apart different protocols. If for some reason Wireshark is unable to interpret the data that you are capturing, you can look for additional dissectors that are out there or write your own in order to accomplish what you wish to accomplish. The Wireshark Wiki has a page here on dissectors and explains how, from a programmatic standpoint, how you would handle designing and creating a dissector. You can see it goes through many of the details in order to do so. Now, this is some great overall information on how you would handle a dissector and what it would do and how you'd go about creating it, but it doesn't actually tell you the individual API data. What you do is you can go to the Wireshark Developers Guide in order to do so. If you look at the Wireshark Developers Guide and you scroll down here to the correct section, you'll see under Wireshark Development we have Packet Dissection. And if we go to Packet Dissection, this will give you an entire write-up on how dissection works within Wireshark and how you can expand upon it with Lua in order to create your own dissectors. Additionally, if you go back and you go down to section 11 down here, you can see here's the entire Lua API reference manual for Wireshark, so that if you happen to know Lua and you're programming your dissector, you know how to reference the appropriate APIs. Now, I mentioned Lua, and Lua is a programming language that was developed specifically for expanding applications and in use in embedded systems. So many applications support Lua as their plug-in programming language of choice. Wireshark is no exception to this. To learn more about Lua, you can go to lua.org, take a look at Pact Publishing, look for any Lua programming books. You can also, on the Lua website, go to their documentation section, and you'll find a link to Programming in Lua. You can see here it's lua.org/PIL. This is a free book that's available to you to learn programming in Lua. Additionally, you can take a look at the Lua reference manual, which gives you even more detail as to how Lua works and how the programming language is created and all the details of how it actually functions, if you need more information than just a standard programming how-to manual. Once you have downloaded a Lua plugin or you have created your own, you can run it in Wireshark by doing the following. If we go to where Wireshark is, like if you remember from the command line video, we're going to go into Wireshark, and if we run wireshark.exe and you look at the help again, you'll see that there is a $X and then there's key and value separated by a colon. This is your extension options, also known as dissectors and plugins. In order to run a Lua script, you can do so by running wireshark.exe $X, then a space, and Lua_script colon the file name. So you're saying run an extension in Wireshark, it's going to be a Lua script, and it has the following file name. Now it's going to look wherever you happen to be running the executable in, which in this example is under program files/Wireshark. So you'll want to put your script into the root directory there or in a plugins folder, and you could do plugins/script.lua or whatever the name is of your dissector. And if you do that and you push enter, it will run Wireshark trying to load that file. Our next video, we're going to get into our troubleshooting scenario. We're going to determine where to capture our traffic in order to best analyze the data and resolve the issue as quickly as possible. Welcome to video determining where to capture. In this video, we're going to take a look at determining where best to start a packet capture for the troubleshooting scenario here. Now, in this troubleshooting scenario, we have a user that is reporting that they are unable to access the FTP server. They start with their client and it just says that the connection does not work. Now what we need to do is determine where we need to begin packet captures in order to figure out what's going on. There might be an issue on the client side, there might be an issue on the server side, or there might be an issue somewhere in between on the internet possibly. Maybe it's a routing issue or something like that that's out of our control. So besides taking a look at log files on the client or the server, we're going to take a look at the packet captures themselves. Additionally, there might be a problem somewhere between the client and the internet, or between the internet and the server. These intermediary devices could be firewalls or routers or something else that might be blocking or causing issues with the connection. With this scenario, since the client is reporting a problem but is not being very specific, we're going to start out with a packet capture on the client side. And then if we determine that we might need some additional packet captures, we will capture on the server side. Normally when you are capturing, you're going to start from the most easily accessible location as possible or closest to the issue at hand, and then work your way along the data path. So if a client is reporting a problem, then you'll most likely try to do a packet capture on the client side. And then if you do not see any sort of obvious issue as to what's going on, then you work your way up. You go to the next intermediary device, such as numbers 1 and 2 on this diagram. And then you go from there, and you might have to get involved with the ISP, and you continue your way along that data path from source to destination, performing packet captures to help determine what the issue is. Our next video, we're going to actually perform these packet captures. Welcome to video capturing scenario traffic. In this video, we're going to take a look at capturing some traffic for our troubleshooting scenario and checking for some obvious issues before we look into the packet capture a bit more in depth. So what I've done here is captured the traffic from the client connecting to the server. And what we can do is put a filter in here for port 21 because we know that the client is connecting over standard unencrypted FTP. So we're going to use TCP port equals 21. That way we get rid of everything else. We see we have 3 packets here, and looks like we have a SYN and 2 retransmissions. So the client, which is .152, is trying to connect to the server running on .160, and it's not even beginning the TCP handshake. So the server is not doing something correctly in order to negotiate port 21. It's not that it's rejecting the user credentials, or there's not some sort of other obvious issue. It's definitely not listening on 21 or something like that. So what we can do is let's start a capture on the server side, and when the client connects, we'll see what it does as well. Okay, we have the server running here, and let's go ahead and try our login attempt. You can see our packets are updating still. The client's still trying to connect, and looks like it has failed. So we'll stop that and stop our capture. And then we'll do the same thing as before. Let's do TCP port 21. And let's see what happens here. So on the server side, it looks identical. So what we're seeing is the source coming into the server as the 152 client, hitting the server's destination IP 160. It's reaching the server at least, so we know IP is working correctly. And we're getting a SYN and then a retransmission from the client and then another retransmission. So obviously something on the server is not running correctly. So since that's pretty obvious, let's take a look and see if our FTP server is even running correctly. Let's take a look at our services on here, and we'll go down, and here's our FileZilla FTP server that's supposed to be running, and oh, look at that. It's not started. So let's go ahead and start this service. Alright, so now our server's running. We know everything looks okay. We'll refresh just to make sure. And let's go ahead and start another capture on the server. And from the client, I'm going to begin a connection. And we can see them coming in here. So we have a SYN, a retransmission again, and another retransmission. The server is running, the service is operational. What we can also do is check our ports that are listening on the server with netstat-an. And let's take a look for port 21. And we see here that we do have port 21 listening on the server, so the service is running correctly. So it looks like we're going to need to investigate the server a little bit farther and take a look at the packet capture once we eventually get this SYN connectivity issue resolved in the next video. So our next video, we are going to dive into the diagnostics of our connection issue with FTP here a little bit further. Welcome to video diagnosing scenario traffic. In this video, we are going to take a look at diving into the captured packets and taking a look at how that FTP server is causing some sort of problem with our connectivity. So in our last video, we took a look at some of the basic settings to make sure that the service was running for the FTP server. We took a capture from the client and saw that there was a TCP SYN with some retransmits, so port 21 was not answering. And then when that service was up and running, we took a look on the server side again and saw that there was still a TCP SYN with some retransmits. So there's still something on the server that's not working correctly. And we know it's on the server side, at least seemingly, because there's a TCP SYN that is arriving at the server. So if it's arriving at the server, it's getting through the firewalls at both ends of the connection. It's getting through the routing on the internet and such. So we know we're getting partway there, but there's something on the server that's not quite right. So once again, let's try a connection from the client, just make sure nothing has changed. We see our TCP SYN come in, and we have another retransmit from the client and another retransmit from the client. And at that point, the client ends up giving up and states that it cannot connect. Since this server is running on Windows, we should take a look at whatever on Windows might be blocking the port 21 from responding. So we know the service is running, and we looked at netstat-an last time. We saw that port 21 was listening, so that's all good, but something else in the system is blocking it. If we take a look at the Windows firewall settings, we see that our firewall is on, and most likely that is blocking it because the FTP server did not put in an exception into the firewall rule. So what we can do is create an inbound rule for port 21, or we can just go ahead and disable it for testing's sake here. So what we can do is we'll turn this off for now. We'll do that on all these profiles. Now let's go ahead and do another connection attempt. I'm going to start the connection from the client. And we see now that we have some FTP traffic. So finally, our client is able to connect partially. And on the client side, it's currently telling me that it wants a password. So we see that we have synac and ACK for the TCP handshake. Then the server responds and says it's running FileZilla's server. My client then requests that it logs in with the test user, and then the server responds saying that a password is required, and my client then acknowledges that request. So now let's go ahead and try to log in with the credentials that the client received. And actually you can see there that I took too long to type it in and it terminated my connection here. So we're going to do that one more time. And if we look at the bottom here, we've got test user, password required again. And let's log in with the credentials that the client was provided with. And I'm now getting an access deny error. So the client still can't connect correctly. After fixing two different things, the client still cannot connect. So let's go ahead and look in our packet capture here and see if we can find out why. So we have our synac ACK. The server responded. We tried to log in with test user. Server says log in with a password. We acknowledge that. Then the client provides a password of 123, test123. And then the server states that the login is incorrect. So what we'll have to do is reset the password in the server. You can see here on the server we're running FileZilla. We'll go ahead into the user section and we will change the password on this to test123, which is what the client is expecting it to be. And let's go ahead and try that connection again. If we take a look here, we have test user, password required, test123 password is sent. The server states that it has now logged on, so that was a successful login with the correct credentials. And we then go ahead and continue with the additional commands that we referenced in the prior videos. What we'll do then is disconnect. And we see from the client, we initiated a finalization, a fin, acknowledge, fin from the server, and then an acknowledge. So we've got the four-way handshake to terminate the connection. So in this video, we were able to successfully diagnose multiple issues with this server. Initially, the service was not running. Then the service was being blocked by the Windows firewall. Then there were incorrect credentials provided to the client. So using Wireshark, we were able to diagnose and provide some information as to where we needed to look, whether it was on the client side or the server side or in between. And it was a great help to us to resolve this issue quickly. In this section, we talked about Wireshark plugins using Lua and creating dissectors. We then evaluated a troubleshooting scenario over several videos, determining where to create our captures, capturing the traffic and doing some basic diagnostics, and then diving into it a little bit more and actually reading the FTP packets once they started to send and receive to the client. We have now reached the end of the course. I hope you have enjoyed your time. In this course, you have learned about the basics of Wireshark, how the interface looks, and an introduction on how to do captures and saving your packets, and doing annotations, capturing from remote interfaces, and so on. You've also learned about customizing Wireshark, changing the preferences of the different protocols and adjusting the interface to your liking. You've learned about network protocols of different kinds, some of the different fields to look at within Wireshark, and some of their behaviors. You've also learned about numerous application protocols, such as the ever-popular HTTP examples and FTP and such. You've also learned about command line options for Wireshark and its various related utilities. And finally, you've seen an example troubleshooting scenario as I went through a series of problems that a client had trying to connect to a server. Again, thank you for watching this course from Pact Publishing on Mastering Wireshark 2.